So, welcome back everybody. If we could start the afternoon session. Hope you all enjoyed the lunch and took full advantage of the ability to look at the posters and displays and talk to some of the people associated with them. As I mentioned first thing this morning, we're very pleased to have with us Professor Sir John O'Reilly. Professor Sir John O'Reilly is Director General, I nearly said Director of General Knowledge, but he's probably that as well. But Director General of Knowledge Innovation in the Department for Business Innovation and Skills. I've known John through many of his recent roles and worked with him. Before his current role, he was Vice Chancellor of Cranfield University. Before that, Chief Executive of the Engineering and Physical Sciences Council. He's a Fellow of this Academy and a Fellow of many others as well. He has served in the past as President of the Institution of Electrical Engineers, now the IET, and he received his knighthood for contributions to science in 2007. It's a great pleasure to welcome John to our forum today, and as I said this morning, his wife is already on holiday without him, so he has to catch up rather rapidly after leaving us this afternoon, so we won't hold him back too long. But John, take the stage.
Rick, thank you for the introduction. It was nice that you ran through those posts. So I had the opportunity to really mess up a research council, to really mess up a university, and now I can mess up the whole lot all in one go. So, but there is something in the title of the job, Director General of Knowledge and Innovation. And that does sound good, doesn't it? It is, of course, all downhill after the title, but we won't go there. What does it mean? I think of it as a kind of three-legged stool in a way, in that the responsibilities that go with this are what we call the research base. So the collection of the research councils and some other things as well, like the UK Space Agency and so on. So that's the research base. In terms of innovation, the Innovation Directorate, the bit that people are most familiar with that, I think, is probably what we now call, thank goodness, Innovate UK, although you might still know it as the Technology Strategy Board. But once again, there are many other things that are important to innovation and other facets, like intellectual property, so the Intellectual Property Office, measurements and standards, so British Standards Institution, and so on come in there. And then there's higher education. Brackets, policy and funding responsibilities for higher education in England. So there's a bit of a caveat there, but there's another caveat, which is, although our policy and funding responsibility is England, we have an interest in it UK-wide, and indeed beyond that. And although it's higher education, we have an interest, of course, in the other dimensions of skills because of the way they play together. But I'm going to focus on those three things of research, innovation, and higher education. And I've put in the observation I've made there. No nation, in my view, that seriously says it's all about a knowledge economy and we want to be in that space can say, let's concentrate and be good at just one of these. It seems to me that to be good at any, you have to make an absolute commitment to excellence in all three. One cannot be good, in my view, at higher education and the things that go with that, without a strong commitment to research and indeed to innovation and the fruits that go through. Similarly, of course, you can't really be excellent at research without good feedstock and close interaction, and I believe the same applies with innovation as well. So that's my three-legged stool aspect, and I'll say a little bit more about that. But in recent years in the UK, we have the new context of an industrial strategy. Mischievously, or cheekily, I sometimes say we've always had an industrial strategy. It's just that until recently our strategy was to have no strategy, or something like that. Not true, of course, but the difference is we kind of nailed our colours to the mast on saying this is really important to our economy, we're going to approach this strategically, and the really important bit is that it is a partnership. It's a whole of government commitment, it's the government with industry working in partnership. I mean, it has obviously some important strands to it. It's seen, by the way, as long-term, so it's not about what do we do that will deliver immediately. Not that there's anything wrong with doing things that will deliver immediately, but actually sometimes you have to go with the longer burn that goes with that. And it recognises the importance of sectors, that there should be support for sectors, particularly support where the UK economy is strong or can be strong, some focus on there. It recognises the importance of technologies that can contribute there, of skills, and so on. 11 sectors have been picked out as particularly important for the UK economy, so it's support for all sectors, but a focus in particular with sector councils for each of these in that partnership mode. So that's context. I won't say too much about the strategy as such. You'll get that elsewhere, but I think it's a very important bit of context in which we operate. I will say something about those three things, and let's start with higher education. This slide isn't quite up to date, but it's close enough for this purpose. What it is three different rankings that are produced globally of universities in the world. The one that we probably know much of for many years in the UK, Times Higher Education Supplement, as I still think of it as, the THE ranking. There's QS, which is a global ranking, and there's Shanghai Jiangtong, comes out of China. Now, they put the universities in the world in a different order. I've coloured the rectangles red or blue according to the country in which that university is. And the really striking thing, of course, is that there are only two colours in the top 10 in any of these three rankings. They use different parameters and different mixes. Nothing is saying these are absolute. It doesn't mean that any of these is necessarily, on all measures, number one in the world. But it does seem to me that if you have three quite separate, distinct rankings of excellence of universities in the world, and UK universities are sitting very high in all of those, then we can be pretty sure that our top universities are very, very good indeed. In fact, disproportionately so if you look at how much red there is that represents the UK and how much blue that represents the United States, and scale it whether it's by GDP or population. So the top end of our system is very good indeed. But in using the phrase top end, I've slipped into that thing that's called the English propensity to turn diversity into hierarchy. We have a diverse system, and actually that diversity is a strength as well. I focus on this bit for very obvious reasons, but had I last year put up the ranking of universities around the world that were less than 50 years old, you would find that the UK sits right at the top of that. So judged against their peers, the UK's newer universities are also very good in world terms. So I think we can say we have some universities that are either very good or have very high reputations, depending on which of these rankings you choose. But not everything's as it should be. And John Perkins, who's sitting here, undertook a review for the Secretary of State relatively recently and produced this report, which I think has usefully got a lot of traction, focusing attention on the problem that we have with engineering skills. We have some very good engineers, but we have nowhere near as many as we need in engineering. And actually for engineering, to a certain degree, read also the physical sciences. As you go deeper down into the school system, the focus rightly is on what's called STEM, science, technology, engineering and mathematics, keeping young people interested in that. But this just underscores we need a good flow of skilled, skilled people through into our economy. Oh, and incidentally, they don't all need to come in through the UK. We do need to be open in that respect, particularly at the top end in research. And we are an attractor for that. When we talk about STEM, of course, there is a lot of promotion of this into schools, to young people, and indeed to society in general. But it's been like that for some time. This is a picture of Faraday in the Royal Institution in his day, and his public lectures attracted huge audiences. Actually, it was a better day, I think, in terms of the public enthusiasm for the Victorian era was a time of this. But we continue with that sort of thing today. To get a feel for just how significant that is, recognise that Albemarle Street, which is where the Royal Institution is, was London's first one-way street. And the reason for that was the queue of carriages trying to get to Faraday's lectures. That was the impact that he had in his day. So there's a challenge there for those who are involved in the STEM initiative, and I know the Academy is doing its bit. When we have to have one-way streets wherever we're holding things, we're getting there, I think. Let's look at research. And these These data have been well promulgated, but I still think we should reflect on them and think what they tell us. We have something just under 1% of the world's population in the UK, but we are a relatively rich nation. So our research funding is more like 3% or so of the world's research funding. That's what we spend. Out of that research funding comes something like 6% of the research papers in the world, but they attract disproportionately the attention of others. They're very highly cited. So if you say what percentage of citations do we have, it's 12% in round figures. If you then look at the most highly cited papers, that top 10% or so, you will find that out of those, 16% of them are the UK. So we have a very, very high-performing research base. This surely tells us we're very good at research. I pause, because in my view what it tells us is that we used to be. I don't by any means mean that we are not good now, but I think it is salutary to reflect that publications and citations that we're seeing today are based on research that was started probably 10 years ago. It takes time for the research to be undertaken, for the publications to come out, for them to attract attention, and for the citations to build. So no room for complacency here. It's very, very good. I'm pleased that they're there, but I do think it's a salutary lesson. This is a retrospective measure of our research. We need to look at some of the leading indicators too. An important facet of research, in my view, and I should say the views I'm giving are very much my personal views, just in case you are expecting anything necessarily to follow from this. But in my view, and I think the view of many others, the dual support system we have is a very, very important component. We have the collective of the research councils that will fund frontier research in the universities, and they provide the project funding, they provide a lot of the funding for PhD students as well, or doctoral students rather. And then in England, through the Higher Education Funding Council for England, there is a comparable, actually slightly larger amount of money that flows directly to institutions, the so-called QR funding, but it's essentially block grant that gives freedom to institutions at institution and department level. To some extent, it augments the Research Council funding to make sure that full economic costs can be covered. But it's rather more than that. It is that important element of freedom, the initial work, and so on. My experience is that dual support is vitally important, particularly to get new things started, to allow the things to be done that when they're sent into a research council, peer review looks at it and shakes its head and said, oh, I don't think so. The sort of thing that on reflection, you might say, I don't think so, and then but if it is like that, if it does do that, then the implications are very great indeed. That's that slightly off the wall, high risk but very high potential return activities, the charting new paths kind of activities, completely new paths in research. And dual support gives us some scope, less than we might like, but some scope for that as well. Actually, I think the research councils and our peer review system provides some scope for that too, but there's always a risk with that, very unconventional, and it can do that. Support for innovation is important as well. And this is salutary or scary depending on where you're sitting. Because that's, actually it's gone up a little bit, but that's essentially the core budget for Innovate UK. In rough and ready terms, I'm an engineer, so I can work to loose engineering. An electronic engineer, by the way. We work to particularly loose tolerances. So of the order 10 to 1 difference, really, between Innovate UK and the research councils. And don't forget there's a QR out there. Don't get too scared, though. That's only one of the support mechanisms for innovation. I've said there are many other things. In fact, if you factor in things like R&D tax credit, then our investment innovation in the UK starts not to look so out of line with some other nations. We're different in the mix, but in my personal view, this is still too small. And the Secretary of State and the Permanent Secretary have gone out on a limb saying doubling that would be a good move. Achieving that is a big hill to climb, but the fact that it's been said, I think, underscores it. But they work together. Innovate UK sits separate from the research councils but interacts with them closely and importantly. As an example, Medical Research Council and Innovate UK have something they call their Catalyst Fund, where they will work together on funding things. And increasingly that is happening. I would say that is a direction of travel that we should expect to see more of and should wish to see more of. I think we should also recognise that Innovate UK isn't just a new name, it's a relatively new organisation. It was formed essentially in 2007, probably. The name Technology Strategy Board existed before that, but that was really a name for an activity within the DTI. It was not an executive, non-departmental body. It didn't have that arm's length from government aspect. And then come the election in 2010 and the closure of the regional development agencies, a lot of things that were done through RDAs were handed to the TSB. So it's been through a pretty cathartic formation. My personal view is it's made very, very good progress indeed, and I think is set to really move fast now. So there's a range of support there. We often say, though, that the innovation bit is the bit we're bad at in the UK. I told you where we were with our universities. I told you where we were with the research. How do we measure up? And again, they're partial views, but how do we measure up internationally in innovation? Well, maybe a condition for innovation, or something that's good to help it along, is collaboration between universities and industry. In my field, in engineering, I feel that strongly. This is one such ranking produced by the World Economic Forum of university and industry collaboration around the world. And you'll see back in 2007-8, the UK was ranked as 12th, 12-13, we were ranked as 2nd. Don't get too excited. The year after that, we were ranked as 5th. That scared me, but it caused me to look very carefully. And there was hardly a whisker between the first 5. What has actually happened is we've moved from a relative also-ran to be really in the leading group on this measure. But it's a partial measure. It's helpful, I think, that we're there. Another measure produced by, it's a global innovation index, led out of the World Intellectual Property Organization and undertaken by 2 leading business schools, one from France and one from the United States, ranks innovation, a composite measure. And again, 2009-10, we were ranked number 14. 12-13, we got the 3rd. And in the most recent ranking, we're 2nd. Don't be complacent, don't get too excited. I can find other measures, if you like, that would not tell quite such a positive story. But the fact that on that measure it has moved up step by step by step tells me we're on a journey in the right direction. And I think a significant part of that is the change that we've made with Innovate UK, the change we've made with the impact agenda, both in HEFCE and in the research councils and in the research excellence framework. And I think it's been a remarkable commitment. If you think back to 2010 and a new government coming in and a comprehensive spending review, the agenda was cuts. Cut public expenditure, balance the budget somehow, at least move in that direction. A remarkable achievement under those circumstances that a flat cash settlement was achieved for the science vote, the ring-fence science vote. It was flat cash so-called resource, and capital was hit rather heavily initially, but nonetheless, quite a remarkable achievement. And since then, at subsequent fiscal events, and fiscal events mean usually the budget time, the autumn statement. Sometimes they're not fiscal events, but party conferences, there are announcements too, but we'll focus on the fiscal events. Subsequent fiscal events saw further commitment to science and innovation. Things like the UK Research Partnership Investment Fund that challenged institutions to get together with business, and actually a 2-to-1 ratio was achieved. For every £1 that government put in, £2 further came from collections of businesses in areas that business thought it was worth investing, a good way of making sure there was good gearing to economic need. David Willis championed what he called the 8 great technologies, and there's been some discussion about 8. There's a very good reason why there are 8, which is that it rhymes with great. And we have the GREAT campaign. Someone told me that at their latest count there are 12 great technologies. So there are the 8 original ones, and there have been other injections since. But a good, strong commitment. And then in the one-year spending review that was undertaken in 2013, so that's for year 14-15, probably the big story there was a long-term commitment to science capital, around about just over £1 billion a year, index-linked out to 2020, whereas all the other budgets had been held at flat cash. We spoke about the 8 great technologies. I assume you know them. They're broad technological areas, and they're areas where the UK has strength and potential to have a strong contribution to our economy as well. But something like 600 million in 2012 and another 180, 190 in 2013. So some substantial commitments there. Quite remarkable, it seems to me. One of the other things that's changed on the landscape, delivered out through Innovate UK, are the catapult centres. Herman Hauser undertook a review, actually for the previous administration, and advocated technology and innovation centres, and this is their realisation. First of all, a multiple site catapult centre dealing with high value manufacturing, but since then others rolled out. We're up to 7. There's another one coming next year which will get us there, and so on. In areas that industry and business see as important. They're not all the same, they're not all positioned quite in the same place in terms of the research, innovation and development landscape, but all strongly linked in to the economy, and actually giving us something in the UK that many of us have looked at other countries with envy, most notably Germany for their Fraunhofer institutes. These are not the same, but let's be clear. What they have in Germany is that which they judge to be right for Germany. That which we have in the UK, we should work to make to be that which is needed for the UK. Located around, clustered, but national centres. So the physical location isn't irrelevant, but they are meant to serve a national need for both large and small businesses. I think I'm going to just kind of reflect a little bit now on this knowledge and innovation space. Research, innovation, enterprise, if you like, higher education skills. As I said, you have to commit to all 3. We have some things that are going on. With 1.1 billion per annum of capital, it would be a little unfortunate if we didn't pay attention to it and come around 2017-18, looked around and said, oh, is that what we did with it? So a little bit of forethought seems appropriate. For that reason, there has been a consultation on capital, and there will be an announcement of what comes out from that consultation at around about the autumn statement time. Of course, the world didn't stop while that consultation was going on, so you will have noticed that commitments have already been made, considerable commitments have already been made in areas where there's something like an international treaty. You either commit to it or you've missed it. So things like the square kilometre array, necessarily, and so on. Also announced is that there will be a science and innovation strategy, and that also will outturn with the autumn statement. I view those as good things, but in a sense it's the fact that they come out that is as important perhaps as the substance, because their very existence is a demonstration of the scale of commitment. And I think that's quite important. We are in difficult economic times. None of us can say what can be achieved in the next administration come the next spending review. All I can do is championship to the extent that I'm able to from where I sit on a desk somewhere in the middle of 1 Victoria Street. But I do make this observation, which I think again is salutary. A flat cash settlement for science in 2010 was a remarkable achievement and a remarkable commitment, and I pay tribute to all of those, including the Academy, that played their part in influencing that judgment. And I think securing that continued flat cash resource budget in 2013 settlement with the increased capital was good too. Let's imagine that we managed to do it again and we achieve flat cash in 2015. Actually, all the noises are that's going to be hard. We're still going to be in a regime of cuts. If you saw Bob Kerslake's recent announcement, he foresees a further 5 years of cuts and says the cuts are going to get harder, not easier as we go on. So whilst one will aspire for more, actually you might think that flat cash is a good outcome when we see what's happening everywhere else. That's not to say it's good enough, in my view. That would mean running out to 2021 on flat cash. And flat cash in 2010 means we're working off a cash budget that was set in 2007. That's a very long time without inflation uplift, yet alone allowing for the changes in technology, the needs and so on, and what competitive nations have been doing. So I'm not saying good, bad. I am saying not easy, but I think it is very, very important that we work together to communicate the vital importance both of the science agenda, the innovation agenda, and with that, the vital importance of skills, as we mean it, that thing which I called the three-legged stool. And between now and the autumn statement, we must make that. But then, as we run through next year, through the election, to a new administration, and what it's probably a comprehensive spending review. One could imagine a short spending review while they gathered breath, but certainly look to that. It really behoves us, I think, to show the excellence of what's being achieved and the importance of what's being done. And I'd like, since I'm standing here, to pay particular tribute to the Royal Academy of Engineering. I was one of those privileged to attend the AGM recently where we elected our first woman president. Well done, and excellent individual by any measure. But I was particularly struck by the three presentations we saw of different things that the Academy does in enterprise, through its fellowships, and indeed the silver medal. I was completely blown away by that, Philip. I'm looking at the Chief Executive down the front here. And I really do urge you to make sure that across government the excellence of what's being achieved is appreciated. And I'll certainly do mine to help promulgate that. I'll stop there, Rick.
Well, thank you, John. John talked about being a champion down the road for science and innovation. I think if we had to pick a champion, then somebody with his background in industry, in the academic system, in government departments, and moreover a fellow of this academy, we couldn't find a better one. So thank you, John, and thank you for your speech. Despite his impending holidays, John's kindly offered to take a couple of questions. Anybody like to raise one? Yes, Carol.
Thank you. Inspiring as ever, John. We have in the past had to deal with quite a lot of capital. What do you think the prospects are for investment that is not so directed around capital?
Well, I'll be very frank. I've said it before, to a certain extent, the squeeze on capital in 2010 runs the risk that we didn't get the full value out of the resource allocations that we made. And then the impulses of capital that came in, with the resource not available alongside it, runs the risk, doesn't it, that we didn't get the full value of those capital. I'm not saying we did, but just let's recognise there's a risk there. So having both in hand together, to me, is really rather important. There is a risk with large capital investments that you overlook the resource demands. And we've certainly got some capital facilities that are running well below their capability, so that needs to be recognised. There might be, and it's only a might, but there might be a hint of something on the horizon that helps. R&D is being recategorised to be essentially equivalent to a capital investment, because it is an investment. And that's being done in Europe. There's now consideration within the UK about whether that is something that we could do. And no promises, Carol, but let's recognise that if that gave us a little bit more freedom across the resource capital divide, then it would matter less precisely how much was put into each. Now, I know that that creates very great problems when you try and run it across government, but I have been advocating, as soon as I saw that come out of Europe, I went in and started advocating this could be a very good feature for science and innovation. But don't hold your breath. So in a sense, I'm kind of agreeing with you that it's a challenge, and maybe, but only maybe, some help there. Certainly, I think the longer-term view of capital is helpful, isn't it? You know, the fact that we know that the capital budget pretty much out to 2020 gives us some freedom of operation we didn't have previously. But maybe that other ability to move the slider would be good.
Another question? Yes. Conveniently close to the man with the microphone.
Sorry. This is maybe more of an observation, but I observe, thank you for your speech, your pillars are research, innovation and skills, and your department is business, innovation and skills. Does this mean research isn't being promoted within the business community? It seems to be that may be a poor
No, it doesn't mean that, and thank you for pointing it out. My responsibilities, so within my Directorate General, we have the research base, which does mean research into universities and research institutes. We then have the Innovation Directorate, and innovation is interpreted in the wide sense. I indicated it reaches quite a long way out into enterprise and so on, but of course it also includes co-funding of research in business and fostering that strong engagement between the research base, the academic bit, and industry. But it won't have slipped by you that I put up the slide about the industrial strategy and said this is the new context in which we should look at the knowledge and innovation space. So that strong coupling to business is very much part of the agenda.
Could I abuse the chairman's right and ask a question myself, John? Where does Europe and Horizon 2020 fit into this spectrum, and how are we going to ensure that, you know, we pay enough into Europe? How are we going to ensure that the UK research base maximises the return to the UK from that?
Oh, thank you. I could have planted that because I should have made that point. Well, first of all, we have a richness now within BIS. There is a Europe Directorate, but that kind of deals with a lot of the other stuff. There's a Europe bit within knowledge and innovation that bolts very tightly into the Horizon 2020 previous FP7 type stuff. And I think there's something important to say there, so thanks for prompting me. The UK did phenomenally well out of FP7. In the last 2 years of the Framework Programme 7, the UK was the largest single recipient of funding from that programme. We topped Germany, and if you look at the relative size of economies and population, that's really quite remarkable. But then if you analyse how that came about, it was the success of academia, of our research base, not our industry. Our industry was less strongly involved than some of the other European countries, and we more than made up for it by academia. Well, I can see academics in the audience thinking that's only as it should be, and aren't they looking smug? All right? But actually it's not good, is it? And when you translate it into Horizon 2020, there is a very, very grave risk, because Horizon 2020 is not the same as FP7. It goes much, much closer to market. It's an opportunity for our economy and for our industries. So it's really important that we engage strongly with Horizon 2020. I'm hoping, I'm challenging the universities indeed, but I'm hoping that they will use their strong network across Europe to help the UK and help industry in the UK to be much more effective there. I think it's a really, really important component. So thanks for flagging it.
Thank you, John. We've got time for one more question. Yes, at the back. Sorry.
Thank you very much. My name is Jerry Byrne. I'm from University College Dublin in Ireland. John, I'm very interested in your thoughts on research and development in manufacturing. Would you have some comments on
that? Couldn't you ask a slightly more general question rather than something as strong? I mean, I honestly don't know how to respond to that. It's vitally important. I'm one of those, and I'd probably use the phrase, and maybe this is as close as I can get to a response. I don't use the phrase pure science and applied science. I don't use the phrase applied research, because I think too often applied translates in people's minds into a pejorative adjective. I adopted something that Bill Harris introduced me to, and which we use in Europe sometimes, which is frontier research. Research for me is about opening up frontiers, moving things forward, and the frontiers are everywhere. So for some people, you know, manufacturing, they say, well, is there a research agenda? If there are frontiers to be taken forward, then there's a research agenda. I don't know how else to respond. It's really important that we develop manufacturing strength in the UK, for me, very, very important that we don't take a narrow perspective of what research is in that ultra-purist sense.
Somebody once
The best
said
that I can do.
somebody once said there are only two types of research: applied research and not yet applied research. So
And it was George Porter.
that's right. So, John, I'm going to draw it to a close there. Let you find your wife and find your family. And,
Great. Rick, thank you.
enjoy your holiday.
Sorry, I can't stay.
Thanks, John. Well, we carry on with this afternoon's agenda, a little later than planned, but there is a bit of flexibility. The panel session can shrink or grow depending on how well I chair what remains of the afternoon. As I said this morning, the next two sessions are designed to be double acts with both the industrial sponsor of the work and the researchers themselves talking about their not only the research itself and how interesting it is, which I'm sure it is in both cases, but the importance of that interaction between the company involved and the researcher, and that's a vital part and a unique part, I think, of the Academy's research schemes. So our first pair of speakers, Dr. Mark Taylor from McLaren Racing and Professor Spencer Sherwin. Mark Taylor is Principal Aerodynamicist for McLaren. He leads a team of engineers and researchers looking at aerodynamic design tools for the Formula One team. He's a fellow of the Institute of Mathematics and its applications. He's actually worked for Rolls-Royce in his past and grew some of his aerodynamics there. So I hope we had some influence on your current skills. And his co-presenter is Professor Spencer Sherwin, who is the McLaren Racing Royal Academy of Engineering Research Chair, appointed in 2012 at the Department of Aeronautics at Imperial College. And Spencer has over 120 peer-reviewed papers, specialised in numerical analysis to applied and fundamental fluid dynamics, and has a very good book on the subject of spectra HP element methods, and I look forward to understanding what they both have to say. Thank you.
Thank you very much, Rick. In fact, Rick was up the chain, my first boss. I joined compressor department in Rolls-Royce in 1998 and got involved with the Trent 500, so we go back quite a long way. I'm here to tell you a story about how we got involved with Spencer in Imperial. What I'd like to start with is describe our business to you, what our technical drivers are, where our research is, and how we got involved with Spencer and used the Royal Academy of Engineering to facilitate that partnership, and how we're pushing the boundaries of CFD technology in Formula One. So the first thing is just to give you an appreciation of the size of the motorsport sector in the UK. I don't think we brag about this enough. We are world leaders in motorsport technology. There are 4,500 companies in the UK, 40,000 employees, 25,000 of them qualified engineers. But more importantly, we're generating 6 billion of revenue, 3.6 billion of which is exported. Also, of fundamental performance is the size of the R&D effort in that sector. So we're doing about 30% of our spend on R&D. Just to give you an idea, compared with what is folklore known as a high-intense research industry, as the pharmaceutical industry, their level of R&D spending is about half of ours. So I'll tell you a bit about McLaren Group. Many of you will know McLaren is a very famous Formula One brand. We've won many world championships over the years. regular race winners, although not at the minute. But just so you know, we have a broad range of activities at our McLaren Technology Centre and Production Centre, which you can see up on the top. There's 2,200 people working at McLaren Group now. The revenues figures you can see, but we've got a total revenue of 553 million. And we're now working in a large range of engineering applications. So the primary one we've got going over the last few years is our road car division. There's a picture of our P1 product. Unfortunately, they're all sold out. But they were a snip at £1 million, so I'm sure one or two of you have had a go at getting one. But more importantly, we have applications across sport. So we've been involved with the UK bobsleigh team. We've developed bikes with Specialized. Many of you will have seen Mark Cavendish win this last stage of the Tour de France 2 years ago on that bike. We also have a large electronics effort, primarily supplying ECUs to the motorsport industry, both Formula One and the US series, but also getting involved in the aerospace industry. And of course, most importantly, we have Formula One, which is the key driver of the business, and it's where we're doing most of our R&D, and the idea is that we're trying to exploit that R&D across the other divisions of the company. So, what is Formula One? Well, it's the pinnacle in motorsport. I hope many of you as engineers are good fans of it. It's technically differentiated, so you win if you deliver the best technical solutions. Drivers are certainly a factor, but it tends to be that the best car wins. There's 20 races a year across the 5 continents, and 8 of the 11 teams are based in the UK, which again I think reaffirms the leadership that Britain has in motorsport technology. They've won 39 championships since 1950, so that is far and away the most successful country. And UK F1 teams and their supply chains employ more than 5,000 people, so we're generating over 2 billion in annual revenue. And this is just to give you an idea about what actually Formula One is. There's a stripped down car. I think when you look at the cars like this, it looks surprisingly simple, although there are a huge amount of parts. There's 15,000 parts in it. But some of the simplicity is obviously for reliability. So this car operates 70% of the time at full throttle for 78% of the distance. So they're extremely stressed devices. Let's give you an idea of the numbers. So top speeds of over 350 kilometers an hour, 0 to 100 in 2.3 seconds. The weight of the car is a mere 691 kilos. That includes the driver. But we're generating downforce figures of over 1.5 tons. So yes, you can drive an F1 car upside down if you're brave enough. And that might be an idea for Bernie Ecclestone's next race. Huge amount of gear changes. And the key thing which makes the sport exciting is the small margins that are between first and fifth, or first even and last. So there's 2% performance gap between the first 10 cars and 0.3% between the top 3 cars. So the margins are extremely small, and this drives our effort in research, because we're looking for the small difference, the small margins, and that's the difference between winning and not winning. So just to give you an idea of what kind of environment we work in, our cars typically got a 6 to 12 month lead time. We've only got 12 days of testing. So we do an all-new car each year. We've got 12 days in a track, and usually a fairly chilly Spain in January. And from then on, we're continuously developing the car. So the car is never the same race on race. So essentially, we get, particularly referring back to my career at Rolls-Royce, the biggest shock to me arriving at McLaren, I started working a part. And when I worked in a part in Rolls-Royce, I was told, oh, well, the rig test will be in 9 months and the engine's going to be released in 3 years. And the part I was working on the Formula One car, was going on in 6 weeks. So our typical time scale is 6 weeks. So you start something, an idea on a CAD screen, go through safety, go to the wind tunnel, go through manufacturer, and you're looking at it on the television 6 weeks later. On the two track maps I have here are Monza and Monaco. And you can see Monaco is very twisty, and Monza's got long straights. So we actually have to re-optimize the car for each track. So the setup and aerodynamic setup for each car is optimized for each track, and this is a key factor in getting those last hundredths of a second that can be the difference between first and second. So, and this is where my department comes in. So I lead the computational fluid dynamics effort at McLaren. And basically our philosophy is that we believe simulation is key to development. So to be able to produce parts in 6 weeks, that's wonderful. But if those parts don't make the car faster, it's a complete waste of time. And the way we ascertain whether we are being successful is by using simulation. So it provides a rapid tool for development. So essentially we model the car. In this case I'm modeling the car. This is turn 2 in Jerez, which is a test track in Spain. We resolve the area with cells and solve the Navier-Stokes equations, which in simplistic terms are basically Newton's laws for a fluid. And then we can produce simulation pictures like I have on the right-hand side, which is a picture of the entropy over the car. We get a three-dimensional view of the flow field, so we can ascertain what's happening everywhere in the flow field. And we can then use it to design better aerodynamic solutions. One thing that has been a problem particularly for me in the last few years, is we've actually been restricted in the amount of compute power we can deploy. So for those of you who are into computers, you'll know about teraflops. So we're restricted in the number of teraflops we can deploy for CFD. And that has been a huge driver in improving the efficiency of our software algorithms and hardware. And that is a factor in wanting to be involved with Spencer, so we have influence on source code, so we can drive the efficiency of the source code to produce answers quicker and more accurately. Then to give you an idea of how we then exploit that throughout the business, I described McLaren Automotive. We also have an applied technologies division where we're applying the technology that developed in Formula 1 into other areas. So you can see, for example, the GT3 version of our 12C car, which is in a one-make race series across Europe. We have the Formula 1 car in the centre. We have track bikes we were involved with a very successful Olympic team, particularly in optimizing helmet design and rider stature. We've done the same for swimming. The bobsleigh I mentioned before, and we've also started to apply it to sailing. So this is to give you an idea of what we can see from CFD. So we can take sweeps through and see what's happening everywhere in the model. In a sense, you can think of it as a virtual wind tunnel. So the engineers, and much of my time is spent looking at videos like this, obviously in a bit more detail because we tend to be looking at a specific design part. And the other thing we can do is by looking at streamlines, we can track the air. So when we're trying to manipulate the air at the back of the car, which tends to have been worked by the front wing, so it's a little more tired, we can follow the particles down and start to manipulate them to deliver performance at the back. And then just to give you an idea about the turnaround, I designed a part that went to the track, and Lewis Hamilton drove it around the track and gave us feedback that it wasn't working in a particular low-speed corner. So I came back on my desk, sort that out. So we performed a safety analysis at the area of the track where the driver had given us feedback that there was a weakness, designed a solution for it, made the car part for the tunnel, sent it to the wind tunnel and tested it in the wind tunnel. Then it went to car build on the Sunday, flew it out to the test on the Monday, and Lewis was driving it on the Tuesday, and he was able to drive 0.3 of a second faster. So that gives you an idea of the timescales we worked to. 0.3 of a second, in simple terms, would be the difference between being first and about fifth. So that's how fast we're working. Now, one of the problems we have is the flow is unsteady. So the images I showed you there were of a Reynolds average solution, and here we have an unsteady flow field. This is actually what's happening. This is a picture of vorticity. The other problem we have is the drivers obviously drive the car, so they move it around. They bounce it up in the air. The tire lifts up. The wings deform. The driver's tire shape changes. So the actual geometry we're trying to manipulate is extremely difficult. And this is one of the hardest things to manage in Formula 1 aerodynamics, is actually to model the geometry itself. And this has been one of the big achievements which Spencer will achieve is being able to create that geometry and run it in high-order codes. This is to give an idea of the key flow features we look at. There's a beautiful picture from NASA of a lifting vortex from a wing, and you just get an idea of the power of the structure that we see in an airplane about to take off. On the right-hand side, I have an image of you have a high amount of swirl and then a peak velocity. So you've got a strong structure that can penetrate the flow. And then down on the left-hand side, you see, again, the swirl, but in the center you see very low pressure. The pink is very low pressure. And these are the structures that we are manipulating in the Formula 1. So by having structures with low pressure, I can put them, for example, under the floor of the car to generate downforce. And being able to model these well is one of our key technology drivers. Here's an idea of a couple of vortices on the car. On the top, you have a pink vortex that comes from the inside of the front wing, and then you have a blue vortex on the outside that comes from the footplate. And you can see we send the two of those right around the tyre. And actually what we're doing there is we're controlling the wheel wake, because we want to stop the wheel wake going under the flow of the car. Down the bottom, I have a picture of what's called a YT50 vortex. It's a vortex at a junction, inboard junction on the wing. And you can see it's massively strong, but also that it's present all the way down the car. So this is why we need to be able to model these structures, which are generated on a 15, 20 mil long flap, and be able to model them for 4 meters, which is a tremendous challenge of length scales management. On the top, you can see how that flow is generated. The wing comes over, the flow comes over the top and gets spun around into that vortex. And this is some work that we did in 2006 with Imperial, and was the actual starter of our relationship with Imperial. So we started in 2003, so it's been a long-term research program. So I hope that gives you an idea of the commitment that McLaren has to research and development. We started this a long time ago, and we're expecting to start using it in designs in the next couple of years. So it's been a long-term commitment from McLaren. In this, we're picturing a vortex that relaminarizes, and this is something where you need extremely high-fidelity methodology to do well, something that's not available in the current tools. And I set myself the challenge of being able to model these vortices in this way, and I had to go to university because the methods were not in existence, and we had to find somebody who could help us do it. So that draws me to my conclusion. We've built a key technical relationship with Imperial, particularly with Spencer, but also with a PhD student who's down the back here. We're developing novel technology, we're applying them. Spencer comes into our office 1 day a week, so the research and the application is directly linked. So we see this as the key way of getting ideas from university into product design. And then we have leverage throughout our business to be able to exploit this technology into other areas like automotive. So I'd also like to thank the Royal Academy for their support for the project. Also Jim McGurk, who's our sponsor, who's helped us a lot. And also to emphasize while I'm here, the key thing we're getting out of this as a sponsor is not just the technology, it's the people. We've hired a lot of people from Imperial, people with PhDs. We're getting the best people in and giving them a skill job that we believe is important for society. Thank you.
Right, I get the job of the dry academic to follow all that Formula One stuff. This starts me off actually reminding that fluid mechanics is very pervasive in all forms of life. My earlier work before we started on the Formula One car was actually a lot to do with biomedical modelling, and ironically this is also a very complex geometry type environment. And if you're a bit unhealthy in this bottom diagram, you might end up with turbulence as well as nice smooth flow. I guess this early points led on to that relationship that Mark was just mentioning. This is actually the second PhD studentship they funded, who looked at not just isolated vortex, but how multiple vortices interact, and he's one of the students they subsequently recruited. So what I'd like to do is step back a bit and remind us why all that glorious technology Mark just showed is insufficient for them to sort of get their next technological edge. And I do that by going back to this slide here and pointing out that although these lovely slices move up and down, the actual image underneath is static, it's steady, it's coming from this average of the flow, and that's what most commercial tools will provide in this sort of modelling. What they require, and Mark was emphasising this point, is the real flow underneath does something like this, where not only is it moving around, it's incredibly unsteady and transient in nature. Now, why is that a problem for us to bring that into our modelling and for them to use it as a design tool? Well, if we go back to the range of what we might know as laminar flow, nice smooth flows you might expect in your arteries, if you increase the speed of that flow, you start to see these smaller and smaller scales. And when we fly and the captain comes on and he's going on about turbulence outside, these are the sort of scales that are involved in that modelling. Now, can we fit all that into a computer? Well, we can go back and ask the questions, how much information can we put on the computer? And to do that, instead of thinking of flow speeds, we go back to this Reynolds number we like to use. Reynolds was one of the very first professors of engineering in the UK. And there are a range of Reynolds numbers. So if I go back to my biomedical flows, that's got a Reynolds number that ranges about 10 to the 3. If we go up to a bird, we might say it's about 10 to the 4. Where we want to be for these car simulations is about 10 to the 6. Okay, that's what he's going to demand and how difficult it's going to be. The stuff that Ric Parker goes, you go into the aeronautic industry, they want to multiply it to 10 or 100 times more, and that might be 10 to the 7, 10 to the 8. Now, if I want to put all those fine scales into a computer, you can come up with a reasonably hand-waving argument, say the number of flops you've got to run scales as this number, this Reynolds number, cubed. And we've all heard of Moore's laws, which are also saying that the rate of computing power is increasing reasonably rapidly at this kind of factor of, say, doubling every 18 months if we're lucky. So where does that bring us? Well, if today we can pretty much model on our supercomputers about a factor of 10 to the 4, if I then want to go up to this factor of 10 to the 6, and I can achieve every single bit of compute in my simulations that they give me through Moore's law, that says that's going to be 2040. Now, I'm getting pretty grey, but that's going to take me to a very grey stage before we manage to squeeze it on the computer. If, on the other hand, we're wrong, in actual fact, I got the scaling, and it takes me 3 years to see that doubling speed in the type of technologies we then apply, then I'm going to slip out having to go back to a lot of biomedical research to survive up to 2070. So this is why in these industrial tools they've got to make some approximation, and using that average type flow is the basic building block technique, and where, if you like, the bottleneck is to go to the next stage of modelling of how we bring that transience back into the picture. So how do we do that? Well, I'm going to give you a brief summary of the type of tools I like to use and why I believe in them so much, but to do that I better give you some perspective on what you could do. If we go back to the very beginning, the basic discretization tools might be finite difference methods. You take a computational domain, you split into little boxes, you use a Taylor expansion, and eventually if you let the spacing between each bit of these boxes come back to 0, you'll get your solution, the real solution that they want for their high-end engineering computing. So that's one approach. Now, the classic approach is to say, if I take a nice periodic box, I could do something like a Fourier transform that we see in lots of areas of science. And instead of breaking into smaller boxes, I could apply Fourier modes and go from a fundamental frequency to higher and higher modes, and that's where I'm going to use this P parameter. And that turns out to be a very efficient way of solving these transient flow simulations, but you can have no geometries. That's not terribly good for their industry either. So the compromise or the balance is then the most widely used technologies in terms of this CFD technologies are either finite element or finite volume, and this is where you can represent a complex geometry, and usually you do it by splitting up into these slightly integral formulations, but you still achieve convergence through making the spacing of this mesh smaller and smaller. So the techniques that I've been developing for nearly 20 years now, I'm afraid to sort of say, is to blend these two ideas. Why do we not try and grab the accuracy of these high-order methods and put them into this geometric complex region to see if we can push the boundaries of what's possible to simulate on our current architectures. So this is my schematic for that type of breakup. Here we have the UK, we can split into triangles, and instead of just putting a linear variation of any of these triangles, which would be these 3 vertice modes on the edge of this plot here, we shove a higher order polynomial, this kind of p-type, this Fourier expansion, into each of those cells. Now that sounds quite complicated. Now why would we do that? Well, definitely the computational cost goes up. As I put this polynomial up, nothing's for free. In 3 dimensions, the polynomial, the computational cost scales as the polynomial to the 4th. But where you can win is the error. How quickly your actually goes down also is very, very rapid. The size of the cell raised to this polynomial order, you immediately see this error become smaller and smaller. So that's fine. That's my initial academic argument, and this is what I go out and I portray, and I tell industry this is the best way to go about it. And they're like, well, that's fine for those academic ivory tower problems. What about the applied problems where I don't need 0.001%, I might only need 10% accuracy? So in a way, we have to go and take a step back and show the following example. If I get a very simple problem and I try and solve the problem with a range of these meshes, as I might do with the commercial type tools, or I increase this polynomial order, what do I see in terms of the performance of that kind of philosophy? So what we see here, there are 2 lines, unfortunately, put on top of each other. If we have a very coarse mesh and no resolution, then that's pretty cheap at least. So this color contours underneath represent the CPU time. So in this corner, no resolution, no polynomial order, cheap. Up in this corner, lots of resolution, lots of polynomial order, of course, got very expensive. The black lines underneath, on top of that, that's the error. That's me saying, well, if I want to be up here, I might call that my academic problem, but this solid line here is what is the optimum choice of this H and P to achieve the accuracy of 10%. Unfortunately, the intricacies of that implementation don't stop there. Most computational methods at the end of the day just end up being a great big linear algebra system, and there are different ways you might fit that onto a computer. You might imagine all the limited degrees of freedom of the vertices of these triangles, make a big sparse matrix system, and up to now we've been able to fit that very effectively onto standard CPUs, where our gigahertz has allowed us just to see an increase in speed over the years. You can also think of different ways of, when I have these little patches of polynomials, of splitting that apart, and I can think of exactly the same mathematical operators in either of these two type of constructions. So underneath, I've got different ways of trying to discretize my equations. And what we are subsequently discovering is the more recent architectures where we now see multi-cores on our laptops, or we hear about GPU computing where you want to use these very decoupled but faster processors. These other strategies allow us to see an accelerated performance. So if I go back to my original map here and I now say, I've got three different types of implementations. If I take my 10% error, can I see any benefit of using these sort of techniques? Well, this is data of the CPU performance along this black line, which is our 10% error line. What we actually see here are the three different implementations I mentioned to you. And what I kind of want to highlight, well, if I use the classic CPU architecture, it tells me maybe I should have used a polynomial order between 2, which is kind of like the commercial discretizations, maybe up to 4, which is actually quite high for them. But as I kind of explore these different ways of implementing it, I see that the optimums tend to get shift higher and higher to even 6 or 8%. And this is for the low engineering, actually. This is not for me wanting to do a very academic, highly discretized problem. So the same way, maybe I should have chosen the same way to show the same sort of example, is to take this problem of a known solution just going around in a circle, which should remain exactly the same, independent of how I choose to discretize it. If I go and use the commercial tools, this is what happens with a relatively coarse mesh. You see how quickly it drops away. This is the numerical diffusion killing off all those transient scales for this 4 meter that Mark would like me to get this vortex to propagate along. If, on the other hand, I blend and I use these P-type methods, I can see at least, okay, I don't get everything, but I keep roughly the shape of the cone. I use this coarser discretization. These have pretty much the same number of degrees of freedom here, but we're able to track it for much, much longer. Okay, so that's my sort of setting before I start, and then I go along, we start a fellowship, I turn up with Mark, and it's like, yes, well, that's all very well, that fancy academic stuff, now we've got to see it in some applied problems, otherwise I'm not going to convince anyone else here that they want to carry on funding you for the next few years going from there. So just to highlight some of the translations or bring it into the industry practice, the first one is, of course, how do we take their starting point? They start from CAD, the next stage is to make a mesh. We interface our numerical tools into their commercial generators, but we have to then play around with them a bit. We want relatively coarse meshes so we can apply this P-type technology inside it. And we also need to resolve these layers very, very close to the surface, which are all important for the aerodynamics they want to optimize and study. So what we've done here is we've taken a very coarse mesh. We're able to curve and represent geometry a lot more smoothly. And we've had to design a bit of technology that in this very fine layer here, we then split it into these finer and finer scales, and I'll show you an example shortly about this is where all the fluid mechanics of the important happens. We've got these very glorious geometries, and in these fine few millimeter scales just above it, we've got to fit in all these discretizations. In fact, in this example here, the below, I'm going to show you what we pack into those little layers. Those 3 lines there are going to come up in this discretization. If I keep zooming in, what we need to have is these small cells, of which I'm going to then put a polynomial order inside, where close to the surface you can't see anything with the eye. Okay, if I can't do that, I'm not going to get any of the aerodynamics back or any of the reasonable solutions. Now, I mentioned we can't resolve everything on a computer, so I don't want to give the example that's also possible today. There are 2 features we have had to add on top in order to make these things actually, well, I put robustness and stabilization. This is one of the demands industry definitely has. It's very well me turning up and running a simulation, getting a fancy answer. What happens if it's just an everyday engineer? How do we make it so they can do it much more robustly and not have to know every little button we've got to push and touch? So one of the issues is with these methods is aliasing. The idea here is that I might have this very high frequency representation, this 20th order polynomial in this example. But if I undersample it, which is what we like to do to try and get computational efficiency, You couple that high frequency back down to the lower information in the simulation, then pollute it, and in actual fact, it usually just blows up, so you don't have to worry too long because you can't even get the simulation. Okay, there's ways we've had to go about controlling that. And then on top of that, we saw the scales in the early animations, how fine local structures you can get in turbulent flow. We are not resolving all of those features, so we have to have a drain, something into the top frequencies, and there's some high-frequency damping we use called a spectral vanishing viscosity. In this example, you can see this initial peak. If you apply the viscosity, you can see how quickly it damps out that very high frequency. That's the stuff we can't model, and that would cause the flow to blow up. But we keep the low-scale structures as untouched and unfettered as possible. So, we bolt that all together. Does it actually do anything useful from their point of view? So I've got two examples to kind of show you to end up with. The first is this NACA wingtip example, which was originally an experimental study at Stanford University. The reason McLaren like it as a geometry, the flow comes in and you get this trailing vortices, and this is kind of representative of the example that Mike showed you of this Y250 vortex they want to propagate for many, many meters down the car. All of this fine structure here, this is the flow swirling in those very fine layers near the surface, and eventually it rolls up and gets this structure as it leaves the trailing edge. What we're seeing on the right-hand side are slices near this trailing edge of a comparison of the forces, of the pressure distribution on the upper and lower surface as compared to experiment. So this is heartening. It seems like we get pretty good agreement with the experiment slightly inboard. As you move outboard, we still get some discrepancies in this region. You can see in the leading edge of the aerofoil, that's in pretty good agreement. So does that make any difference between the tools they might use now in their commercial environment? Well, I take the same test case and we use a commercial solver, and what they might be interested in seeing is how well can we maintain the velocity in this direction as we track back down this vortex core. That's what this line represents. So as I move downstream away from the body, this is what the experiment tells us we should be achieving. If we go and use the commercial tools, that steady flow with this turbulence model underneath it, the most simple but widely used turbulence model is this K-epsilon model, we get some pickup but very quick, rapid drop-off. And that's what they can't now use to say, I want this to propagate down the car and do something fancy further downstream. If we go and run our simulations using the spectral HP element techniques, we're seeing a much more heartening correlation with the experiment in terms of how well we maintain the intensity of that vortex. And I guess to be fair to the turbulence modeling community, there are fancier examples of turbulence models, of which this last line represents this RSM, which is the Reynolds stress model. But the problem with the Reynolds stress model, at least I understand from their point of view, is if they go and consider a more fancy example, they can't get it to work all over the geometries. So this is my last example. I've got my 1-minute warning, so I think I'm nearly getting on time. Okay, so this is our most recent attempt at a much fancier geometry of applying these high-order techniques to flow over a Formula One car. This is the hardest or most complex geometry I've ever tried, and as far as I'm aware, for these methodologies that we use, that's ever been simulated up to now. Now, what do we see? We see a lot of this red and blue colouring. This is helicity. This is how the flow is swirling as it gets pushed along in the streamwise direction. Now, we've instantaneously in the movie, this is as far as the animation, the simulation has currently got, have ramped up from 10 times slower speed in the wind tunnel up to the wind tunnel conditions. And what you kind of observe is the flow, or this noisy flow that they'd like to control, is swept back over the wheel. If I press this button, we'll get to see a blow up of some other regions. And what we get an impression of here is what Mark and his team spend a lot of time trying to design. All over these front wings, they've got these funny little geometries coming out at different directions. What they're trying to do is produce things like this. Here's a, I'm going to get this wrong, the end plate maybe vortex, it'll get a foot plate vortex. And here's another example looking inside outwards, where again, as it powers up, as we increase the speed, we see on the inside of this wheel, this is a scallop vortex, if I can get this one right, of how it turns into a nice uniform red colour. And what they want to do is force that vortex to come past the wheel and control this mess, this noise that does all the horrible things to the back of the car. So that's kind of where we're getting to in terms of demonstrating. This is about a 10-year-old geometry. I'm not allowed to do anything on up-to-date geometries, otherwise they burn all their teraflop limits in one go. But now that we build up the confidence of using these type of techniques in this example, then we see to try to translate that into the design practice. Okay, so in my summary, we've kind of got these turbulent flow simulations. It's certainly a highly demanding HPC application that requires, but that has a variety of uses, not only in the aeronautical, but certainly, not only the automotive, but also the aeronautical field. And transient flow modeling is kind of the state of the art of where we're at when we talk about CFD. We have a lot of commercial tools for this average type modeling state. It then requires an awful lot more compute to go to this transient modeling. But if we can get the right tools and build the confidence in the engineering environment, then they go ahead and try and design even fancier designs for either their cars or the aircraft. Okay, I'd also like to reiterate thanks for both the Royal Academy of Engineering and, of course, for EPSRC to have helped fund a lot of this research.
So, many thanks to Mark and to Spencer. Fascinating presentation, and clearly, as Mark I think conveyed, a huge UK industry, not just a UK sporting success, which is how many people think of Formula One, but a huge UK industry that's being facilitated by this partnership established under the auspices of the Academy. Next, we're going to look at a different area yet again, laser applications. And this is, again, quite an unusual partnership. The very first Fraunhofer institution outside of, or in the UK, so Fraunhofer have established Fraunhofer Institute in the UK, and that is itself teamed with Strathclyde University. So our speakers are Professor Martin Dawson, who's head of the Fraunhofer Centre for Applied Photonics at the University of Strathclyde. Professor Dawson is also Director of Research at the Overall Institute of Photonics in Strathclyde University, and he was a founding member of that back in 1996. He's also, since October last year, 2012, the inaugural head of the new Fraunhofer Centre there. He's over 30 years of experience in this field and has made significant contributions in laser technology and semiconductor optoelectronics. His co-speaker this afternoon is Professor Alan Kemp, and Professor Kemp is the Fraunhofer UK and Royal Academy of Engineering Research Chair as of this year, starting 2014, in Advanced Laser Engineering. Alan joined the Institute of Photonics in August 2002 as a researcher, and he had a research fellowship from the Royal Society of Edinburgh, which set him on his way, and he's done other industrial liaison with Thales and Scottish Enterprise. So no stranger to industrial partnerships, but again enabled by the Academy and the contributions from Fraunhofer to take up this latest position. So I'd like to hear from Fraunhofer.
Thank you. Good afternoon, ladies and gentlemen. It's my pleasure to be speaking at today's event and to give you an overview of the status of Fraunhofer in the UK, but also why we've partnered with the University of Strathclyde and the Royal Academy of Engineering in supporting this research professorship for Professor Kemp. So many of you in the audience will have some familiarity with the Fraunhofer organization, but this just briefly summarizes its core base in Germany. Of course, the name Fraunhofer comes from Joseph von Fraunhofer, who was a scientist, discovered the Fraunhofer lines in the solar spectrum, for example, but also worked very extensively on the quality of glass as one of his key areas of applied research, leading to a range of optical instruments being formed. And so he's a very appropriate person to bear the name of this organization, which is about applied research. So the organization is headquartered in Europe and is very substantial. There are 67 institutes and research units operating in Germany. I've highlighted the Fraunhofer IAF in Freiburg there. whenever a Fraunhofer Center is created outside of Germany, there's a partnering mentoring institution, and this is the one that mentors us. And I'll come back to discuss that in a little bit more detail later. But okay, it's well known that the concentration of the Fraunhofer organization in Germany. What is less well known is that this is progressively becoming an international organization. And this shows a list of the current status of formal Fraunhofer subsidiaries around the world. You'll see, for example, the United States. There are 9 centers or institutes there. And in fact, this very weekend, they're celebrating their 20th anniversary of being founded. And of course, there's a new kid on the block here, Fraunhofer UK, which I'll give you more details on as we progress. It's important to say that these are the countries in which there is a formal legal entity and a formal subsidiary of the Fraunhofer organization. If we look more closely at Europe, we'll see that there are other forms of interaction with Fraunhofer internationally, joint research projects, project centers, and so forth. And in fact, many universities in the UK already interact with Fraunhofer in various ways. But a kind of step up in operations happen when a legal subsidiary is created. And in 2012, Fraunhofer UK was established with its headquarters in Glasgow. And the Fraunhofer Centre for Applied Photonics, Fraunhofer CAP, which I head, is the first research centre operating under that legal umbrella. So very briefly, this is the history, if you like. Fraunhofer didn't come to the UK by accident. It came as a result of a process of engagement started by Lord Drayson in 2009. And then there was a lot of interest from UK universities in engaging with Fraunhofer, and a kind of beauty contest took place that, for various reasons, we in Glasgow at Strathclyde ended up being the front runner to create the first organisation. And Fraunhofer UK Research Limited was formally registered as a not-for-profit business in the UK in March 2012. And then Fraunhofer CAP launched October 2012 with myself as head. So 2 years in is where we stand at the moment. And in fact, we had one of our formal launch events here at the Royal Academy of Engineering in May of last year. So what's the current status of CAP, the one research centre that Fraunhofer is currently operating under the umbrella of Fraunhofer UK? Well, just to emphasise again, the Fraunhofer model is a not-for-profit model operating units as independent research and technology organisations. We currently have 26 staff and students involved, so from a standing start back in October 2012 to that level at the moment. And one of the key aspects of the Fraunhofer model is that the incentivization starts on day one. There's nowhere to rest, and you have to keep pushing. So it's very pleasing that we've got a significant number of projects through in the first 2 years. In particular, you'll note that TSB Innovate UK has been a very, very important source of funding, as has the EU. And one of the nice things at the moment is, actually with a recent award, we can say for the first time that the competitively won projects that we're engaged in, the total value of those exceeds the initial core startup investment. So that's a very nice position to get to in 2 years. This is all based around real labs, real technical capability. The Fraunhofer approach is that its own engineers do the commissioned company interfaced applied R&D. And so these labs have been established, and the operation is focused around business units, and the first business unit we have is in solid state lasers, and I'll discuss in a moment the reasons that area was chosen, but also the interface to Professor Kemp. So I've already mentioned that when an overseas Fraunhofer Center is established, there is a mentoring institute in Germany that holds your hand and helps you learn the ropes. And in our particular case, it was the Fraunhofer IAF in Freiburg, and they continue to help. My university base is the Institute of Photonics at the University of Strathclyde. And so the first thing we did when we were discussing the development of this new photonics Fraunhofer Center was to basically compare expertise. And we compared our sort of block capabilities, as you can see there, and also took into account where the local and UK-wide industry demand fitted into this. And out of that came the core focus for this initial phase, at least, of CAP on solid-state laser engineering. So it was not by accident that laser engineering was chosen. There's a very long history of excellence in that area throughout the UK, and a particular concentration in the central belt of Scotland, spin-out companies and other organisations there and elsewhere to benefit. And these all basically allowed the picture to come together. So many of you know something, or perhaps more than that, about how Fraunhofer operates, but I thought it was just important to emphasize the particular approach that Fraunhofer takes. Fraunhofer is there and exists as a not-for-profit organization to serve industry. That's its fundamental objective, but it does so from a very close interaction with a university. And a distinctiveness of the Fraunhofer approach is that the head of the Fraunhofer Institute or Center is a professor at that university. In my own case, I've been at Strathclyde for 20 years and then had the opportunity to also head up this Fraunhofer Center. But the professor is there to really manage that interaction. And you can see there, I've tried to list very briefly what the benefits of that approach are. The Fraunhofer organization, the operation, gets academic alignment and reference from the university, exposure to new and emerging research and ideas very quickly. It's part then of a very closely managed, or ideally a very closely managed, applied research pipeline, which is two-way, of course, university to industry, industry to university. The closeness to the research sector keeps Fraunhofer and its operations relevant for the long term, which is very important. The university interaction is an ideal way to both help to train employees and to employ those trained people when they graduate, and in fact to help them in an applied research form of PhD or engineering doctorate training. And further, universities often have local industry and enterprise clustering around them, which Fraunhofer can engage with. So this is, as I said, we started from scratch 2 years ago. This is the current staff, and it's perhaps worth emphasizing that 13 of the 17 have PhD or engineering doctorate level expertise. And this is a very enthusiastic and committed group, and it's a fantastic privilege to be leading them. So where does Alan and the university's expertise in solid-state laser engineering fit in? You could say what we've done in the creation of Fraunhofer CAP is combine together various elements of capability that have been developed in the universities in Scotland and elsewhere over many decades, and put them all together in one industry interfacing package. So we have our own core areas of expertise. Alan brings in complementary expertise with his particular focus areas, which he'll describe and which I'll say a little bit more about just in a moment. So without embarrassing Alan too much, I hope to warm things up a little bit for him here by mentioning a couple of the themes I know that he will focus on. So the first, and this was the primary, I think, technical area that he focused on in his in the process of gaining his RAN and Fraunhofer supported chair, is diamond as a laser material. Diamond, of course, is a fantastic thermal conductor and has many uses in lasers just to extract heat, but it perhaps isn't as well known in general that diamond, in fact, can be a laser material in its own right. You can make diamond lasers, and these particular lasers, as Alan, I'm sure, will describe in more detail, are based on a process called Raman scattering, stimulated Raman scattering. One of the features of diamond is that it's very transparent over a really wide spectral window. And so in principle, you can make a very, very versatile, wavelength versatile laser technology out of diamond. And I just wanted to show here one example of the type of work that Alan undertakes to really underpin that work. Clearly, what you need to know in order to make these lasers operate is something about the gain characteristics of the diamond Raman process, which scales with wavelength. And the setup on the left and the results on the right show the summary of a very, very thorough and painstaking investigation into the wavelength dependence of that Raman gain. And this is the sort of thing, in my 30 years as a laser researcher, this makes my heart melt, actually, because this is beautiful work, very, very thorough. And this is one of Alan's characteristics, that he picks up a problem and won't let it go till he's actually thoroughly investigated all aspects of it. So this is an essential underpinning design capability for exploiting this wonderful engineering material as a laser technology. And I should perhaps say that this work benefits from an industrial linkage as well with element 6. We're very fortunate here in the UK that we have the world leader in the manufacture of synthetic diamond, and we've worked closely, and Alan has worked closely with them for a number of years, so they're involved in this. Second one, I don't want to steal Alan's thunder too much, to mention is this second example. The titanium sapphire laser is a workhorse laser technology, a very, very important commercial one used in many, many scientific and instrumentation applications. Alan has been working on a simplified and potentially lower cost way of pumping these lasers. And again, a characteristic that he brings to bear is that using diodes, as this approach does, to pump sapphire was for a long time thought to be impossible. And it's a tribute to the thoroughness with which he understands and investigates the underlying principles of the operation of these lasers that he's found a way to make this work. And you can see here again, Fraunhofer has engagement here and company involvement also. And you can see as well that there is funded work in this area between us under support from Innovate UK. Oops. So finally, I just want to summarize the mutual benefits and enhanced opportunities that we think, we in Fraunhofer think has come about from the support of Alan through this Fraunhofer FREng research chair. To Fraunhofer, we get the benefit of exposure to Professor Kemp's research. We get extended and broader university interactions and collaborations for opportunities for collaborative R&D. Of course, we can identify very able new staff that we may wish to recruit. We can also identify through his work students that we want to draw in, either to have work in our organisation through their studentships or to follow on. And we also bring the pipeline from university to industry and vice versa. For Alan himself, he obviously will tell you his own views, but I believe that the benefits include the following. So he can be exposed to industrial R&D challenges through the Fraunhofer interfacing organisation. We also provide extended ways in which he can pursue and support his own applied research. We have dedicated facilities and equipment, not necessarily available within the university, that he can access. there is the chance to experience the discipline of Fraunhofer as an industry interfacing and supporting model, and of course the links to the wider Fraunhofer network, and as I've already mentioned, new ways of student training that our operation offers. So we're very proud and pleased to have been able to contribute and support this chair, and to join with the Royal Academy of Engineering to promote and support UK engineering excellence. Thank you.
So, thank you very much, Martin, and thank you to the Royal Academy of Engineering for the opportunity to speak today. What I'm going to do is try and add some detail to Martin's presentation and say a little bit about the way that Royal Academy of Engineering Research Chair funding and the links to Fraunhofer have allowed us to exploit the synergy between two. Excuse me, I don't have them there. Exploit the synergy between two research teams within the university and in Fraunhofer CAP to not only allow us to increase the impact of our research, but also to scale up our effort both at the industrial interface and the underpinning laser engineering research that we hope will be the seed for the next round of industrial interaction. So I shall start by saying a little bit about one particular area, which is the dial-pump titanium sapphire lasers. This is one of our as a particular TSB project, or sorry, an Innovate UK project, as Martin mentioned. It's one of a range of instruments that we use in order to interact with industry, and that the links to Fraunhofer allow us to do that. Other examples would be industrial doctorates, some based at Thales, some based in Fraunhofer, interacting on industrial projects, and also direct interaction with industry. And I'll say a little bit about that around the diamond work and working with a UK company who are the leading manufacturer of diamond in the world, and that's element 6 in the second half of my talk. So back to titanium sapphire lasers, and as Martin mentioned, these are in many ways both the workhorses and I would say the thoroughbreds of scientific lasers. They have underpinned or the tools that have underpinned, for example, a number of Nobel prizes, and that's because they're very adaptable systems. They can produce both very short pulses and very wide range of wavelengths. But I guess part of the price that you pay for that is these are sizable laser systems. They're table-sized systems, and they're very expensive. In the excuse me, I don't quite know if that's happening. They're very expensive systems in the sense that they might cost £50,000 to £100,000 a piece. And part of the reason for that is the pump laser source shown here. To pump a titanium sapphire laser requires a laser to begin with. It's a two-stage process, and that is shown here. This is a standard industrial pump source for a titanium sapphire laser, and it's a rather large system and probably cost of the order of £30,000 to £40,000 even before you've built your titanium sapphire laser. Now, a lot of lasers we're able to pump with diode laser technology. This is the big brother of what we would find in a Blu-ray system. These are a few £100 a piece, and as you can see, it's sitting on top of the other laser. It's considerably smaller. But the conventional wisdom always was that the physics of titanium sapphire meant that this wasn't an approach. You needed this larger mainframe laser to pump titanium sapphire. So starting in about 2005, we had a closer look at that issue, and we began to suspect that maybe changes in diode laser technology and a little bit of careful laser engineering might mean that conventional wisdom was really no longer true. And in 2009, in fact, we were able to demonstrate on the lab bench that was the case. So this is the first directly diode laser pumped titanium sapphire laser with output powers that are beginning to get into the regime where they become interesting for things like optical microscopy and these sort of things. I guess only interesting for optical microscopy if you can also produce these very short pulses, which are characteristic of titanium sapphire. So here's an example. If there are any laser people in the audience, they'll recognise the autocorrelation up here. It's a measurement of the pulse length, and this particular pulse is about 100 femtoseconds long, so 100 times 10 to the minus 15 seconds, very short event, and that allows us to do many very interesting things with these lasers. And so we're now working, funded by Innovate UK, working with a local laser SME in Glasgow, M Squared Lasers. They're leading this project to try and take that technology and exploit the fact that it's cheaper and it's smaller to maybe build systems that can now go inside a microscope rather than sitting separate to the system there. And so I'll move on from the work that we're doing perhaps at the current industrial interface to the work that we're doing hoping to prime in the future the next industrial interface, although I should say that this is already very strongly underpinned, as Martin has mentioned, by interaction with Element 6, who are based in Oxfordshire and, as I say, producing the really world-leading material that we're able to support, that supports the laser engineering that we're able to do. So before I go into why diamond is interesting to a laser engineer like me, I maybe have to say a little bit about why the management of heat is important in solid-state laser engineering. I mentioned there the titanium sapphire lasers, so we had one laser pumping another. So if we look at the titanium sapphire laser rod, here, for example, we'll find that we're depositing heat in the center of a rod of crystal, and we're removing the heat from the edges. So we set up temperature to edge thermal gradients in that material. And that leads to stresses and eventually to material fracture on the one hand, but also to changes in refractive index in the material and to lensing. And it's these thermally induced effects that limit our ability to scale the output power of these lasers if we want to maintain that pencil of light, that very focusable beam that we associate with a laser. So one of the big challenges in laser engineering is to remove heat effectively from our laser material. And that points us towards high thermal conductivity materials, materials like diamond, for example. And here diamond is compared to a number of conventional laser materials. And you can see that the difference in thermal conductivity is not a small change compared to the materials, the sort of kit of parts materials that we're currently using in laser engineering. It's a step change. And so you might ask the question, why haven't we been using diamond for many years in laser engineering? And the answer to that question has to do with the reproducible optical quality of the material that was available to us. And that has really changed since about 2005, ramping up perhaps in 2010, where we now have material that has not only very low losses, but also very homogeneous optical quality, so very low birefringence in the terminology of laser engineering. And that combination of qualities has been brought together, as I say, in the UK by Element 6 in Oxfordshire, and it's that material that's allowed us to exploit diamond in laser engineering. So this is a summary of diamond as compared to a conventional laser material, the sort of textbook material, yttrium, aluminium, garnet, YAG, where I've put the numbers for YAG here in green and the numbers for diamond in blue. As I've already said, the thermal conductivity is very much higher, but notice also that the mechanical properties of diamond are far superior to those of our conventional laser material, something we'd also like to support. As I mentioned, the big change for us has been that the optical quality of this material has improved remarkably thanks to the diamond synthesis community, a lot of which is located in the UK. So I'm not taking any credit for that, but the UK certainly can take credit for making this material, I think, credible in a number of engineering areas, but certainly in laser engineering. So there's a problem that remains, and that's really a but, if you like. If we want to exploit this in laser engineering, really we would like to provide optical gain in that material. In our conventional oxide crystals, what we would do is dope it with neodymium into YAG or titanium into sapphire. But you can see that these ions are bigger than the carbon-to-carbon spacing in diamond. This is a very compact crystal lattice. This is very hard to get these materials in there. So that means that we have a situation where we have a material that we'd really love to be able to use, has so many very attractive properties, but there's a missing piece in that jigsaw. Thank you. And what we would want to do is to add some extra abilities to diamond around the area of being able to amplify light. So either to do that indirectly by using diamond to cool a conventional material, or directly using some novel approaches of Raman scattering or colour centres in diamond. And that's the area that we're working on. Also, there's a parallel process in terms of much improved technologies around processing of diamond that I think has also become very important as we move forward. So these are some examples of diamond-enabled lasers from the Institute and from the Fraunhofer Centre, and I hope to convince you in the next few minutes that this is in fact a very poor use of a high-quality laser engineering material, and that we'll be far better off using this for technological applications. Okay, so one example of how we might use diamond is in a semiconductor disc laser. This is a laser that Martin, amongst others, helped to pioneer. And here, removing heat is crucial in obtaining high performance. And it's a geometry that's very well suited to diamond because we can get the heat out of a very thin layer of semiconductor material very quickly into diamond. And that means that diamond has become crucial in enabling groups around the world to obtain watt-level laser performance over a very wide spectral range with these devices. And that's, I guess it's the area where diamond has made its biggest impact so far in solid-state laser engineering in many ways. But as I mentioned earlier, what we'd really like to be able to do is use diamond directly to provide laser amplification. One way we can think of doing that is using Raman scattering rather than conventional stimulated emission. Raman scattering is the scattering of light off vibrations of the material to reach a shifting light to a redder wavelength. There's also a stimulated analog of this that allows us to do coherent amplification and hence to build a laser. And in I guess a very nice Royal Academy of Engineering funded collaboration working with my colleague Dr. Jennifer Hastie, who's a former Royal Academy of Engineering research fellow. She and I and our teams were able to demonstrate the first tunable diamond Raman laser by combining semiconductor disc laser technology with diamond Raman laser technology. And this is an orange system tunable over about 15 nanometers. And so I'll say maybe to close off a little bit about where we would like to go in the future. Raman lasers have a lot going for them, but there's some things that they can't do. One of which, for example, would be probably to generate the very short pulses we associate with titanium sapphire. And so we would like other ways to generate amplification in diamond. One way is to exploit so-called color centers in diamond. The laser engineers in the audience may be familiar with color centers as something in the alpha halide crystals that are quite difficult to work with. The nice thing about color centers in diamond is that they're stable up to well above 1,000 degrees centigrade. These are a very much different system in terms of their environmental response, but they produce very broad emission spectra in the visible region in a host matrix that is has very attractive thermal and mechanical properties. So perhaps if we can learn how to exploit these in the future, there's potential for a new generation of visible titanium sapphire lasers at potentially at much higher power. As I say, there has been one demonstration back in 1985 of a system based on color center lasers in diamond from Hughes Research Labs, but that research didn't go anywhere because of the quality of the material. And the quality of the material really has changed by orders of magnitude in the last 10 years. So this is something that we hope to revisit in the next few years. So just to finish up, I'd like to maybe re-emphasize the point that we have a very interesting material here for laser engineering. We're looking for ways to exploit that over a uniquely broad front, and I think the ability to work over a broad front is supported by the research here and by our interaction with Fraunhofer in a way that we couldn't do without that interaction. And it's also enabled us to bring in the industrial interaction much earlier in the process than we would have been able to do otherwise, already working with companies like Element 6 on this. And perhaps in the future, this is a direction that may help the laser engineering community move towards taking these very highly functional lasers, with the sapphire type equivalents, into forms that are simpler, more compact, and potentially more powerful. So just to finish off, I'd like to thank people that have funded this research, particularly the Royal Academy of Engineering and Fraunhofer UK, and companies like Element 6 who've been instrumental in providing the material for this. Thank you very much.
Down the gap at the back.
Right, thank you for that. Again, a fascinating talk, an example of yet another type of collaboration between a research institute, admittedly a legal entity, a non-for-profit organisation, and university researcher, obviously doing great things, but with the added outreach that Fraunhofer itself has to industry to cause further research collaborations. So very interesting. We've got time for just a few questions. We must start the panel session soon, but I will allow time for a couple of questions, hopefully for each of the pairs. So he has a hand up straight away. I'd like to.
This is Charles Dickerson from Loughborough University. I have a question for Mark Taylor. Does McLaren consider aerodynamics the primary design feature for winning Formula One races?
Yes.
And they do. Okay.
Full stop.
And given that positive answer, what's the secondary design feature?
Well, assuming you have an engine that works, which has been a challenge for one or two of the teams this year, but the engines are very tightly regulated. Most of it is coupling the behaviour of the car, so how you set it up suspension-wise to optimise the aerodynamics. So one of the challenges we have is developing aerodynamic solutions that can cope with low-speed corners and high-speed corners, where you can get changes in wind direction to the car because of its own motion of up to 20 degrees, so plus or minus 10 degrees. So having aerodynamics that are insensitive to that range is a major challenge, and then setting the car up to be able to exploit that is the second.
I'm sure the drivers might have something to say on that subject, isn't it?
They're jockeys.
How they might contribute.
Please don't quote me on that.
Yeah. Next question, yes.
Hi, this is Thomas Nowotny from University of Sussex. This question is for Spencer. I was wondering, you mentioned GPUs and the use of GPUs for CFD in your talk. Can you give us an impression how you're using it? Is this with linear algebra packages that exist, or are you doing your own code?
It's within our own code. I mean, part of the challenge there is making there's enough compute to do on the GPU versus the interconnect, right? So increasing this, playing with this polynomial means there's a lot more compute per cell. So in that sense, that's why it gets disguised. You know, we've all got this balancing act. So pretty much these days, whereas before when I used to have my presentation, that was a big worry that there was all this compute and that's why it scaled poorly. You don't see that on most modern architecture performance. We've got very compact coupled piece of information that we can do a lot of work on, and then we've got the challenge of everyone else of shoveling it around and making sure that part's efficient.
Yes, please.
Yes, John Fisher. I'd just like to ask the two fellows if, from their perspective, the advantage and distinctiveness of the Academy Fellowship in comparison with, let's say, a fellowship from senior fellowship from one of the research councils or an advanced fellowship from the ERC. Just a little bit more from your perspective on the distinctiveness of the Academy scheme.
Would you like to start off?
I think, from my perspective, the most distinctive feature is the built-in link with the partner, and that's been very important from my perspective in terms of allowing me to scale up a research effort rather than doing more of the same. It's allowed me to work over a broader range of topics.
I actually held a EPSRC Advanced Research Fellowship a few years back, and so the distinction I would draw, that was very useful, of course, in the development, actually having to get the science and getting the stuff done. This has been much more motivating at a particular point in the career of wanting to engage with the industry, turning up and working that much more closely with them, and then also pointing out where beforehand I might have been worried about one aspect. When you see their design cycle or their challenges, it helps you reorientate, you know, how you're going to put all the challenges in the correct order for them. So that's been quite striking and also quite invigorating, if you like. You carry on doing the same sort of mould. You recognise a certain pattern to it, you know how you go about it, and have your PhD students here. There's a sudden injection of, okay, a completely different environment, and want to see translation into practice.
Any more questions? Just, yes, on the right.
With these GPUs and things like that, Mark, how do they actually keep track of how many gigaflops you're allowed to use? You said you were limited on the...
Oh, and the teraflops of the computer.
Teraflops, yes. I mean, it seems like a very hard thing to actually...
So what they do is...
Train you to.
It is very constrained.
Run something on your PC that Spencer's developed.
So what we have to do is, if we make use of a CPU, and the length of time we make use of that CPU, we have to declare the potential teraflops of that. So it's not actually the number of teraflops we use, it's the potential teraflops of the chip. So each job that we do, each simulation that we do, we have to deliver a log file to the FIA, which they then inspect. And we get audited once or twice a year.
And that's why GPUs aren't terribly popular at the moment in that environment.
I'm going to just ask one quick question to our colleagues from Fraunhofer. I was particularly impressed by the rate at which you'd got successful funding applications through from a standing start. Question, firstly, is it something about the Fraunhofer process that does that? And a question to our sponsored academic, do you find the Fraunhofers particularly stern taskmasters in terms of writing proposals, or do they take a lot of that weight off you?
I think to answer the first part of your question, I suppose, you know, we're very keen to make a success of it. So the enthusiasm is there to really kind of go for it from day one. But also the model itself is one that really requires success. So you have to try, and it's very heavily incentivized. So there's a discipline associated with the framework that we're working in. But also the fact that it's been started from scratch here in the UK, it's drawing on a lot of enthusiasm as well.
So to answer the second part of the question, I would say the beauty of working with an organisation like Fraunhofer is the speed with which they're able to move is much better matched to the speed that industry would like to move at. So even in things as simple as you know, hiring a researcher to undertake a bit of work, they will have typically have someone they can allocate to that, which just brings the timescales of moving academic research into industry much closer to what industry really requires of us.
That's a model I shall watch with interest. So. Good. We're going to go straight into our panel session now. There's no break. We're heading straight on towards the end. So we've got about an hour for the panel session. Could I thank the four speakers for the afternoon? It's been a fascinating session. And could I ask our panelists to take their places alongside me? What you do, disappear down this gap at the back. Yes.
To assume that we sit in the order in which we're in the programme.
What was your title of the building research?
Yeah, then I will sit next to you. I'll sit next to you.
Oh, bit important bit.
Move along then, I think. No, there's...
Hi, Bob.
Hi.
Welcome.
Sorted ourselves out.
Something to scribble on as
well. Right, well, welcome everybody. We're in the home straight now, as they say. We've got 5 eminent speakers in our panel. I'll very briefly introduce them. The topic we chose for the panel is quite timely. It's research impact. Is it really important? And as I said in my introduction this morning, given that the REF exercise has this time around has a major component that was based on impact, and as you'll see, some of our speakers have been intimately involved in that process. Others have been the subject of it, and yet more will be customers for its outcome. So we will see how that goes, and I think one of the challenges for the panel will be trying to get us onto a common base in all understanding or seeing if there is a common definition of impact or if it's still all things to all researchers. Firstly, on my immediate left, Professor John Fisher, CBE and FREng, is Deputy Vice-Chancellor of the University of Leeds and was the chairman of the EPSRC and Royal Academy of Engineering evaluation of impact in engineering research and training. John's the first deputy VC at Leeds. He supports the Vice-Chancellor across a large range of activities, and he's also the director of the Institute of Medical and Biological Engineering and has an active role in leading research in medical engineering. Welcome, John. Second, next to John, is Jeremy Watson. Keeping up with Jeremy's biographical details is always a a challenge, and they'd changed between being printed this morning and the time he arrived. So I'm pleased to announce that John, as of Monday, is now the Chief Scientist and Chief Engineer of the Buildings Research Institute. So congratulations on the new appointment. Jeremy, sorry, not John. Jeremy is holding that new post. He's had a number of fascinating roles. I first met him when he was Director of Science and Technology at Arup. In parallel with doing that job, he was also for a while the Chief Scientific Advisor for the Department of Communities and Local Government, so he had to keep Eric Pickles under control, which is no mean task. He was awarded a CBE in the 2013 honours list, so welcome, Jeremy.
Thank you.
Third, our industrialist on the panel is Bob Sorrell. Bob's from BP, and he and I have spent many hours discussing university and industry interrelationship. Bob is BP's Vice President for Public Partnerships and Associate Director for the BP International Centre in Advanced Materials. This centre, set up a couple of years ago, is a vast 10-year and $100 million investment by BP. The hub of the institute is in Manchester, but it spans the world, including Cambridge, Imperial and the University of Illinois. So a major piece of industry and university interaction. Next to Bob, and our lady member of the panel, welcome.
Yes, there are some of us.
There are. Professor Carol Goebel, again CBE and a fellow of this academy, is Professor of Computer Science at the University of Manchester. She's Principal Investigator on the MyGrid BioCatalogue and the My Experiments projects, and leads the Information Management Group. Her research on knowledge and information management has taken itself into what's called the in silico science and scientific publication and creation area. So getting out of in vitro and into in silico, so something to look forward to. And last but not least, an old friend and colleague, Professor Steve Williamson, fellow of this academy, until recently the Deputy Vice-Chancellor for Research and Enterprise at the University of Surrey, now a gentleman of leisure, except for when he's working twice as hard as he ever did doing that. He was chair of one of the REF panels, sub-panel 13. He is a fellow of the IET and the IEEE and also of this academy, as I mentioned. He has a number of distinctions. He's currently a non-executive director of Tesla Limited and also is the chairman of Rolls-Royce's Electrical and Control Systems and Electronic Systems Advisory Board. So welcome to our panel. They're each going to be given 5 minutes to talk on the subject of, without repetition, deviation, or...
repetition, I guarantee.
I have to repeat between each other, but to talk on the subject of impact, and then we'll throw it open to the floor for further discussion and questions. Okay, should we start from left to this end? Do you want to start?
Yeah, that's fine. Well, I think it's, seeing that I'm first person to speak, it's important to recognise there are essentially two definitions of impact. There's a very broad definition that has been developed by RC UK, which I would call both academic and non-academic impact. And I think there's the more precise and possibly relevant definition of impact that's been used more widely by the Higher Education Funding Council through the Research Evaluation Framework, which is essentially considerations of impact of research from a university perspective outside of academia. So let's put that in brackets, a non-academic impact. And I think it's the non-academic impact or the HEFC-REF definition of impact that I'll certainly use in introducing it today. And I think the first thing I would say is, which probably gives away my point of view on this, is I always use the term research and impact, not research or impact or research impact. I use the term research and impact because I've always felt that impact, innovation and impact is an essential part of the research agenda from a university and academic point of view. I think I'd also say, just referring back to John O'Reilly's presentation earlier today, I would also add to that education and research and impact are essential bedfellows. They are intimately connected in an academic or a university system and closely related and form a very virtuous circle that in effect it's hard to do one without the other. And of course the thing that connects education, research and impact is of course people, and it's the development, education and training of students who feed both the research base and of course the engineering employability, and they are the people of course who often go on to create the impact outside of academia in many different forms in terms of translation of their knowledge, their skills, translation themselves into the wider environment. And I think that's how we've got to think about impact. In academia, in universities, you always seem to be posed with questions that give you choices, certainly as a Deputy Vice-Chancellor. People will come forward to questions, what's more important, education or research? Or what's more important, research or impact? And I think what my point of view is in this system, they are all very important, and it's the synergy between the three that makes the university system so important and so valuable. But I wanted, just in terms of supporting the case for my point of view, to say that research and impact is very important, could possibly never have been more important than now, and that's one of the reasons why I took on the chairmanship of the EPSRC and Academy group that's looking at evaluating the benefits and impact of research and training. Is to try to make the point through two examples. The first example I'll give is an example over the last couple of years in my role as a member of EPSRC Council, in which I chaired the group that put together the programme for the Centres of Doctoral Training. The Centres of Doctoral Training was a programme of 60 CDTs across the country, which was coming up for renewal, and we had the opportunity to look at what the new programme would be for the next 5 years. And that's a programme that's been announced recently. And it was clear under the flat cash scenario that John O'Reilly talked about going forward that 70 centres that were funded in 2009, under that scenario would end up as 50 centres that were funded going forward to 2022, simply because of the flat cash scenario and the impact of inflation. So we took a view in that situation that actually these could be much more than research and training, and took a view that we wanted to have substantial engagement with industry partners and other non-academic partners to develop those centres. And as a result of that approach, we geared the call for those centres in a particular way that we required support from industry for collaboration on research and training for the PhD students at a level of around about 30% of the direct costs of the centres. And that proved to be hugely successful in engaging industry, and the call was extremely successful, and by doing that we were able to support 80 centres initially. But the success of that call was recognised by government, and then in the end we managed to raise additional capital and recurrent funding directly from BIS, which allowed us to fund 110 centres. So we went from a scenario on flat cash that perhaps we might have ended up with 50 or 60 centres. We now end up with 110 funded centres. And those centres are, I would argue, doing research training, and also doing impact. And I think that's the point of research and impact, because if you really embrace that concept, then actually you open up a whole range of other opportunities to enhance the research environment in the universities and in the country. I've probably done my 5 minutes, so I'll stop then.
Very good, John. Thank you. Jeremy.
Thank you very much. I was going to address the question really from the point of view of a number of lenses, which I've, if you like, ways of looking at things that I've had the benefit of working with. So the public sector, the higher education institution sector, I'm Vice Dean of Engineering at UCL at the moment. The private sector, the importance to industry of the impact from particularly engineering research, and indeed from the Research Council's point of view, because like John, I'm on the EPSRC Council at the moment. And those lenses give rise to the need to appreciate that impact actually has more than just a scalar dimension. It's a vector of values. And I think it's important to think about the obvious immediate economic value, but also the knowledge value, the development of people, the development of the national position in the world, which John O'Reilly alluded to, the general social good, and then the knock on the interdependencies between research and the infrastructure that supports research in the rest of the country, both in industry and in academia. So particularly thinking of engineering research, which is rather naturally associated perhaps with economic outcomes by the nature of engineering, I think it's important to value and understand the need for balance in our strategy around that, and certainly within EPSRC on councils, although I'm now probably more of an academic engineer than an industrial one. Most of my time actually has been in industry, and I worked, most of my professional development was done in BOC, the gases company, British Oxygen, and I recognised as a consumer of research the real need to balance between the pull on our needs, which were market-based, but also keeping a very careful eye on the emergent knowledge that was coming out of serendipitous or blue sky or basic or whatever you want to call it research. And I think it's vital that we keep that absolutely in the national eye in terms of public policy, that there's a synergy that's really important there. And if you look at some of the major advances that have had huge economic impact, and I think particularly of the laser, which goes back to Mayman probably 60 years ago. I haven't done the research on the exact date. For many years that sat on the academic shelf as an interesting
64.
64. And now in our homes we probably have, I don't know, 20 or 30 lasers, don't we? Communications, disc reading, lasers, everywhere you care to think. So that was, if you like, a serendipitous piece of work that was curiosity driven, that's probably had a trillion-dollar, multi-trillion-dollar impact. Fibre optics are the same thing. Against that, we have to balance the incremental research that's pulled through, say, telecom, cellular phone technology. And it's really down to, I think, the professional institutions, obviously importantly, government research councils, to make sure that we keep the emphasis right in those areas. So I think that's a really important point. The other thing is really the enabling factor of research on supply chains, and obviously Ric's company is leading in that. So innovation in big companies, which may largely be based on market pull, but also through very effective university partnerships, tends to nurture and seed ideas in the SME and the bigger than small enterprise community that serve them directly. So there's a great leverage effect there that I believe is very important. And I just thought I would reflect briefly, I'm not being too aware of time here, the experience in government where research had a totally different meaning, if you like, and certainly the part where I was working, where the appetite for evidence wasn't uniform, let's put it that way. So I would say that, you know, my experience, starting with the Chief Scientific Advisor's experience, it was difficult to get ministers to understand the value of research sometimes, and I actually had to write a paper about the value of research, would you believe, and the key phrase I just extracted and made a note of was, research is about reducing uncertainty. Uncertainty is associated with risk, and risk is with exposure to cost. So a rather negative point there, but I'm going to end on a rather more positive one. I think, you know, so where is the future? Where is the future impact? Engineering is a wonderful interconnecting mechanism, I think, a discipline that automatically is multidisciplinary, but actually it can reach out still further into across the system's view of things, and working with disciplines like the social sciences, understanding how things like aesthetic form influence function, and ultimately can we assist society by designing interventions that produce desirable behavioural outcomes like energy efficiency or whatever that might be, through the way we both do the design and the engineering work, and I think that will be the ultimate impact that we can achieve. Thank you.
Very good. Bob, where are you taking us?
Okay, so maybe I'll provide a little bit of in perspective and pick up on some of the other comments I've heard as well. So as Ric alluded to in his introduction, you know, I've been involved with Steve on REF main panel B, and as an industrialist that's been a very interesting experience. I'm also on the board of Innovate UK, so I'm also at the kind of customer end of impact as you pull technology across. And then I sit in the middle, outside my BP role, as a non-executive director in a very small technology-driven startup company. So you can see, impact showing up through all kinds of different lenses. So, if I think about the exam question here, why is research impact important? I think, most scientists and engineers want to see their research being used. And I think, impact for me is just one manifestation of that. I think how we define impact is important here. I mean, from my perspective, we can talk about commercial, but there's also the issues associated with research informing policy and research also engaging the public in terms of scientific awareness of some of the issues we're facing, which I think is an increasingly important issue, as particularly in the energy area, as we move into all kinds of interesting debates about new technologies, the impacts of climate change, etc. So, having agreed that it's important, I think the thing for me is it's an issue really of balance, and I think it's really absolutely critical that we preserve the balance associated with what I described. I think we talked about blue skies, curiosity-driven. I would call it fundamental research. And if I look back from when I was doing research in a laboratory, the last university was Durham doing that. Frankly, now I'd just be dangerous in any laboratory doing research. And I look where we are now, 3 decades on. There's been huge advances in science. You look at the increases in modelling, characterisation, imaging, synthesis. And so now we're able to do things today and look at things that were just completely unthinkable of 10, 20 years ago. And so for us, if I just step back for a second, from an energy industry perspective, we're able to look at the fundamental science behind issues that you'd think we would deeply understand, but actually we don't. Things like corrosion, things like hydrogen embrittlement that reduce hard steel down to the quality of a powder. So how is that happening? And I think one of the really interesting things here is because we can now, through modern application of these technologies, whether that's characterization, imaging, whether that's the synthesis, we're able potentially to get a much better handle on what's actually going on, to understand the fundamental science, and then behind that we can really begin to develop some interesting paradigm shifting solutions. So I think when we talk about impact, we have to be very careful about the timescales over which impact plays out, and we have to exhibit some patience. And certainly, in my industry, if I look at that, the way that things play out is they play out over decades, and it's a long period of time over which these changes occur. But I would really, really strongly defend a position where we preserve that curiosity-driven, that fundamental research element. And I think you can see that there's been a shift not only in my company, but in a whole range of industry sectors to much deeper relationships with university partnerships. When I started 30 years ago in BP, we had our corporate labs in Sunbury. We have dismantled those and allocated those now out across the businesses. And we have replaced and in fact we've created an innovation ecosystem whereby we leverage the technologies we have with the academic partnerships that we form. We talked about one that I look after. We have several of these, not just in the UK but across the world, and they really all focus on probing this fundamental understanding of science, and it's absolutely critical. And actually we believe fundamentally we do far more through those partnerships than we can just working on our own. So my final point would be the kind of coming back to the REF exercise, which, frankly, as an outsider getting involved in it for the first time, I found to be absolutely fascinating. I think what's really interesting is we've generated a whole series of case studies, and those case studies have been verified effectively by industry and by academics. And so we've got a great big body of work here. And if I step back and put my business hat on, I would say, this is a great basis for an investment case in science for UK PLC. And let's not waste the opportunity of being able to use that, because at the end of the day, what we want to do is to be able to encourage companies to base their translational, their R&D activities here in the UK, because effectively that creates more jobs and wealth for UK PLC, and then it reinforces the argument about why we should be investing in science in the first place. So on that positive note, I'll stop.
Thanks, Bob. Carol.
So when you're fourth, lots of people have said many things you wanted to say. but nonetheless, so I'm going to take a personal view. So I'm actually a engineer, a computer science engineer, and I do e-science. So I'm very much at the applied end of John's research strata. And in particular, I work in Europe on providing infrastructures for European research. So I'm part of a big thing called Elixir, which is the infrastructure for bioinformatics across Europe. I built the biodiversity virtual laboratory for biodiversity, which feeds into policy for government. I can tell you why crabs are invading the Baltic, but I won't. And I'm also serve on the BBSRC Council. So I serve on the BBSRC Council as a computer scientist, not the EPSRC Council. So I'm a technologist who is looking at impact in other areas of science, and particular is progressing that impact through infrastructure and the translation of semantic web technologies, distributed computing technologies into those. So I'm quite interested in the idea of impact that is not necessarily commercial, but is impacting nonetheless significant scientific advances. So I slightly disagree with the notion of impact outside and inside academia. And I had this problem when I did my ref, because I might build platforms that thousands of scientists use, but they're scientists and therefore they didn't count. And but if I had one dodgy SME that used it, that would be okay. Now, of course, I exaggerate slightly, and Manchester is very good at writing refs, so we dealt with that. But there is some issue here. There is an important point to do with the kind of special place that we placed on commercial exploitation and commercial impact. There are other forms of impact. Particularly, I've worked extensively on standards, and there's nothing more like a standard to be absolutely highly influential and deeply invisible. So again, we have to think of a way of being able to surface these, because as a researcher I need to also report my impact, and that's quite tricky, but quite tricky as well when you're working in large-scale collaborations, which you must do if you're engineering large-scale infrastructures, if you're doing important translational research. I also wanted to raise the point about time. Dino and Helen this morning talked about foundational work that was laid over 100 years ago in the logics that they're now using. I'm sure Pierce wasn't asked what his immediate return on investment was of his abduction logic. And in fact, the formal methods I was very interested to see. I married a formal methods man. He taught me formal methods when I was an undergraduate. That's how I met him. I'm a computer scientist. I'm very efficient. Marry the lecturer, get it over with. And I'm quite old. I was, Dino was born after I was taught that, and it takes a long time, even in computer science, which is one of the fastest spinning technology and engineering environments or disciplines that we work in. So you have to give things time. And you don't actually know what will make an impact in the end. Did we think abduction, do we think description logic would be a key fundamental of how we represent knowledge in linked data on the web that drives some of Google's knowledge graph? No, we did not. We did not expect that. So finally, I would also like to mention the fact of building up this stable link. If we are going to link with particularly commercial enterprises, I am a major player in a IMI, an innovative medicines initiative called Open Facts, which is with 10 pharmaceutical companies building a knowledge platform for pre-competitive drug discovery. And that's been terrific. It's a stable environment in which to do fundamental knowledge transfer of semantic web technologies into pharma. It was started up by a group of far-sighted leaders in the pharmaceutical companies who saw that open innovation would be critical. And you ask yourself, of the, I think it was 10 who originally started up, how many of them are still in pharma? And I would tell you, 1. Because pharma spins so fast at its way it spits out its staff. In fact, Pfizer fired everybody to do with information management just before we started the grant. that really this makes it extremely difficult to build a stable environment to do the knowledge transfer, to do the impact. So impact works from academia to industry if there's somebody in industry to catch it. And often we are not working with a company, BP, AstraZeneca or so on. We're working with somebody in BP, somebody in AstraZeneca. And if that person gets switched out, then you're no longer working with them again. So on that bummer note, I'll turn to my colleague.
So, Steve, if you're fifth, there's nothing left to say, but I know that won't stop you.
It never has. Okay, I'm, I think, fundamentally in disagreement with Carol.
Excellent.
I'm an engineer, an academic engineer, and all of my career I've worked with industry, and I think it's right and appropriate that, I'm not a physicist, I'm an engineer. And engineering is all about making products, it's all about making and improving products, and I think as an engineer, my research should have impact. Now, that doesn't mean it's all going to have impact, but I would expect over my career some of it has had impact. And I think in answer to your question, Carol, there is no requirement for all research in universities to have impact. For the REF, for example, the universities had to produce one example of impact over a taking place over a 6-year period for every 10 academics. That isn't a requirement for every academic, all of their research to produce impact. So there's still plenty of scope for blue skies research, which I'm also fundamentally in support of. But I'm also a taxpayer. I'm no longer paid by a university, but I am a taxpayer, and so I want to see my tax money being used to have impact on UK industry in particular. I also had as it says in the script, I'm currently still chair of one of the sub-panels. We don't wind up until November. But I've also chaired a similar panel for the exercise in Hong Kong. And that's been quite interesting because in the quiet times, I talked about the UK exercise and the fact we require impact. And all of the academics present did exactly what all of the academics did in the UK about 3 or 4 years ago. There's a nursery story about a Chicken Little, or Chicken Licking, who runs around saying that the sky is falling. And they all ran around basically saying the sky is falling, this is never going to happen here. And I will guarantee, I'll take $100 Hong Kong bet that the next RAE in Hong Kong includes impact once they see how excellent our exercise has been. My panel had about 150 case studies to look at, and we've seen some superb examples of impact from leading UK universities. Now, these are all going to be available for everybody to look at on the hefty website, I think sometime around about March. I can guarantee that they're going to be mined by government. I can guarantee that John O'Reilly will be using them to make his case for at least flat funding. At least flat funding. I think it's a major source of the arguments that our politicians, who aren't always the most far-sighted people, will use. And they will use that to support the research in UK universities. And I think that's tremendously important. So, by and large, I think impact is a good thing. I think that's all I want to say.
So do I.
Well, that's got it off to a fiery start. Good. I think just to referee between the two at the end, I think certainly you would expect engineering research to have engineering impact. Disappointingly, there was one director of the research councils some years ago who should have known better. It wasn't John Riley, it was two previous to John, if people want to work out a name that goes with that, who came out with the atrocious statement, there is no such thing as engineering research. So debate. But I think what we've seen this morning, and what is fascinating, is the number of times that non-engineering disciplines do something that finishes up having engineering research and being adopted by engineers and shamelessly cribbed and claimed to be their own, but never mind, it still has impact. So I'd like to throw it open to the floor. You've heard 5 different and differing views on impact, its importance. It's the impact of impact, if I put it that way. I think certainly I agree with the panel that as a result of doing this exercise, we have created a huge stock of case studies, more than just the usual anecdotal case studies, but real case studies of how investing in research can turn into wealth and value for the UK and can turn into societal impact. As somebody said, impact shouldn't just be measured in commercial terms. If it saves lives, if it stops the planet overheating, that's still a good outcome from a piece of research, even if it's more difficult to put a pound note value to that. So who wants to start the ball rolling with questions to the panel? Feel free to direct it at the panel as a whole, or if there was something an individual said that you want to pick up on, then direct your shot with great accuracy at that individual. Yes.
William Harwin, University of Reading. Actually, I just want to follow that up with a couple of points. Our university's actually gone back and looked at the case studies that we put into the ref and found out that actually policy was one of the biggest areas where we were creating impact. And are we missing in engineering? We tend to be very focused on economic impact. Are we missing a trick here by not trying to hit and identify the policy impacts that our research might have?
I would say no, because I saw such impact case studies. So some universities have done it, if yours hasn't.
Jeremy, yes.
Yeah. A little bit of a sort of a plug for the department I work in. So a new department in UCL called Science, Technology, Engineering and Public Policy. And of course there are other policy groups in other universities like SPRU in Sussex and CSAP in Cambridge. I think there needs to be more focus. I think the point is well made. There is a lot of impact available to government from universities, and having worked in a department when I was a civil servant which downsized by 40% and lost most of its specialists, there's a real need for external inputs, and there is indeed an appetite for those inputs. So what university colleagues need to kind of just get an appreciation of is the form in which information is best received by policymakers in government and the route to reach them. So I think it's very important we recognise that.
I think we're knocking down an old building recently in our Bristol site, and at the back of one of the machines there was a brass plaque that must have fallen off the wall many years ago. We don't know exactly who wrote the quote, but from the phrasing, I think it was Sir Roy Fedden, and it says, making policy on the basis of doing what's technically right is not necessarily wise. Making policy without knowing what's technically right is fallacy. And I think that's probably where our impact on policy should come in. It's certainly, in this past year, been quite an increased area of debate within the academy. How do we influence policy? Are we set up and structured in a way to have enough influence on policy? Is it our role? Are we a lobbying entity, or are we the deliverer of facts to government based on our colleagues in the academic world supplying us with those facts? So it's a topic we have been mulling over, and I think you're right, the impact on policy is a very real and important impact of our universities. Next question. Yes.
Thomas Nowotny from the University of Sussex. It's for the general panel. If we assume for a moment the narrower definition of impact, and then by definition is outside academia and outside what academics do, is it wise to require every academic to do a lot of stargazing outside of what they normally do to basically document their impact continuously? Or are they wasting time that they could be using for research?
So would academics be better spending their time getting on with good quality research rather than worrying about whether it was any use or not? Yes. Who'd like to pick that one up first? Carol, do you want to?
So one of the things I was impressed with the talks this morning, if I put it in that context, is that all the speakers were undertaking really important core research, but they were doing it in context. So they understood the wider function of their work, and they were working in an ecosystem. And I think that's still important. So I think everything I do has some sort of impact. It may not be an immediate commercial short term. It may have a long-term impact or may influence some other research group. But nonetheless, I would like to be sure that what I'm talking about and what I'm researching on has some sort of transferable effect somewhere. Now, I guess what you're saying is it important for me to constantly think about how I might commercialize this, for example? And I find that I must admit, I find it difficult. I've solved my problem by giving everything away free. So I give everything away open source. So when my intellectual property partner from the university arrived, I'd already given it all away. That saved me having to worry about it quite a lot. But it also means that I have tremendous actual impact. So the effect of doing that was that people use it, and the people use it in new ways I didn't expect, and some of them have partnered with me so that we can do new innovative work, things I would never have thought about. I didn't expect to work on the virtual physiological human. It turns out that's what I am doing. I didn't expect to build library preservation engines, but in fact that's what I've done for the British Library. So by making that kind of statement, by having impact in that kind of way, I've kind of done exactly what I think that you would appreciate. I just chose not to do it through wrangling around intellectual property. So I think it depends on how you want to be able to think. How will I do impact? I don't think you can completely ignore it. You shouldn't ignore it, but you should mindfully think about how do I choose to do it.
John, do you have a view on what's the feedback from your academics? Did they find it a waste of time and effort, or are they taking something positive from the exercise?
Well, I think it's right to say it's not for everybody. You know, there's a range of academics, there's a range of research, and academics will be doing different types of research. I would say generally the people that have been engaged in the process of developing case studies have really embraced it and found it very rewarding, and I think it has and will influence the way they do research in the future. I don't think it's a additional bureaucratic burden going forward. In fact, I would say for the people who choose to get involved in doing research and impact, which necessarily means they start to engage in their research with others outside the academic community, I think the real value that comes in is there are then a broader set of perspectives on the research questions that are being set and asked and addressed in universities, and I think that's probably the most important part of this impact agenda. It's not in counting what's produced going out, it's about having some influence on setting the research questions that are being addressed.
Yeah.
Bob.
So I've just turned the question around a bit really, and rather than kind of focus on commercialising stuff, I would look at understanding some of the really interesting challenges we face in industry today, and then whether you commercially exploit elements of that, well, that's a separate issue. But I think there are a lot of really interesting challenges that are out there today, and many of these challenges span multiple sectors. And Carol began to touch upon it. You know, with the big things we look at, like advanced materials, big data, they transcend the boundaries of individual sectors. And the thing that we're finding actually in this partnership that I look after is that they're also beginning to pull together partnerships, if you talk to the academics involved, that they just wouldn't have expected in the first place. And so they start to link up pieces and actually, you know, pursue this academic curiosity to work on things together. And as a consequence, you get some really unexpected results and some really unexpected people coming forward to talk to you about things that they might like to do. Yeah, and I always think that not everything is going to be commercialised. After all, if we knew the answers, we wouldn't do the research in the first place. That's what our chief scientists always say to us, and it's true, isn't it? So I would just turn the thinking around the other way, really, when I think about this. Yeah.
Steve.
Yeah, I'm almost worried about the nature of the question. 10, 15 years ago, we were told that multidisciplinary research or interdisciplinary research at the boundaries was a good thing to do. And a lot of academic colleagues were really concerned because they thought, well, interdisciplinary research, good, within a discipline, bad. And it wasn't, that wasn't the case. It was interdisciplinary research, good, sole discipline research, also good. It was trying to get people to think more and do where appropriate, multidisciplinary research. And I think that's the same with impact. You don't have to do it, think about impact and do impact all the time, or impactful research. My advice to any researcher is to pursue the things that are interesting to you, and good will come of it. And that's the key thing, because one of the beauties of universities is that this idea of academic freedom. To my mind, academic freedom is not the freedom to decide not to do research, but it's the freedom to decide what you want to research on. And you've got to follow that, follow your own instincts and your own interests, and don't worry too much about it, and good will come of it.
I think, reflecting on what Bob said, my old professor said to me one day that as an academic he used to spend half his time thinking up the answer and half his time thinking up the question. The advantage of working with industry was you were bombarded with questions and therefore could focus all your time on the answer, which was actually the fun bit. So I think that's how I would see it. Right, there were several hands went up there. Lady on the right here, yes.
Stephanie Hayward from the University of Hull. I'd like to pick up what Carol said about having the importance of having somebody in industry to catch what you're doing, to make that connection. But I'd also like to praise the Royal Academy, because I actually think that what these schemes do is actually formalise that link, so that you have got somebody there in a formal manner to pick up that research that you're doing. But I have certainly had the experience over the years, quite often, that I've started projects with somebody who's very enthusiastic in the company, and either they've moved on to other jobs, or they're just under very significant time pressure. So outside the big companies like Rolls-Royce and BP, smaller companies are often under pressure actually to deliver, to answer that question that you were talking about. And the company that I'm working with at the moment through an industry secondment is actually very dynamic and growing from a medium to a large-scale company. But they've recently got a new CEO, and my first worry was, will that person want to continue the collaboration beyond the Royal Academy secondment? I mean, fortunately they do, but I think it is a real problem, and the more that you can formalise that collaboration and make it part of the company's strategy through schemes like that the Royal Academy run, the more impact we'll have of the industrial and commercial type.
Good comment. Any specific response? Or, yes, Jeremy.
Yes. Oh, sorry. You go ahead.
Well, I think the question was to you, wasn't it?
No, sorry. Yes, it was. You're right.
I'll take second. Yeah.
So I totally agree. The most successful of my commercial knowledge transfer activities, if you will, is through the Innovative Medicines Initiative, which is a formal framework in order to be able to bring together the pharmaceutical companies and vendors to the pharma environment. And that formal framework was critical because it meant that when there was churn amongst individual partners and partners also leaving and joining, that was all managed. That there was opportunities to pick up, to smooth out all that churn, and that collaboration has proved to be incredibly successful. But I completely hear what you're saying about the number. We've all had stories of the contract was about to be signed, and then the CEO resigned, and then the whole thing fell to pieces, and then that was another year, and which time we've lost the postdoc, and the PhD students graduated, and we're done. So, and this is why the Royal Academy of Engineering and also the Royal Society does similar things, but particularly the Academy does these excellent initiatives. I sit on the panels that dishes out the fellowships, and I know how important that work is.
Jeremy?
I was going to reflect on the fact that sort of being both a poacher and a gamekeeper, if you like, in the same domain, and also recognising the the difference between the absorptive capacity of a big company, where it's largely a high-level sort of political decision whether you carry on with an academic, and a small to medium-sized enterprise, where in fact the input might be very, very strong meat for them. They may be very focused on what they're doing, and this is where knowledge transfer partners have demonstrated some real value. But even they, in a very small company, can be just too much, I think to take on. I think there is something, again, as a recipient of research outputs when I was at Arup, one of the things, when I was funding a doctorate, for example, we did a lot of work with NGDs in particular, was to expect and hope for outputs that were through the course of the PhD, so that the NGD wasn't just a case of waiting for the thesis at the end. It was the relatively informal, come and do a lunchtime presentation, tell us about your literature survey right at the beginning so we can start to look at that as well, build up that sort of synergy, and which hopefully will help the researcher as well. And I think the final reflection really is the importance with key partners, just as EPSRC has strategic partners with certain universities and certain companies. So companies and universities can very effectively form those longer-term partnerships through maybe an MOU of some sort, which defines the way in which they're going to work together, not just research, but also education, maybe some joint policy making, those sorts of things, business even, together. That can give rise to a more enduring relationship, I think, and de-risk some of what you've mentioned.
The gentleman had his hand up just there, two in from the left.
Ranjan Banerjee from City University London. Now, on the question of quantifying impact, can I ask the panel, how do you quantify impact both in qualitative and quantitative terms? Can you give us some insight, some indicative guidance? How do you quantify impact?
You want to start with that one?
Well, I'll start with it by saying it's difficult, and we all know it's difficult. And it's the very question that we've tried to address through the working group from the EPSRC and the Royal Academy in terms of the report we will produce in January on the value of engineering research and training in the UK. That will be based on economic analysis and two different forms of that. So there's some sort of method development to try to see whether we can use new methods to try to get a better indication of the economic value. But what's emerging in that is what's been referenced earlier about the REF case studies. We've managed to draw together 500 REF case studies in engineering from 20 universities. We've had a group of consultants look at those, and I think it will be the first analysis of an integrated approach to REF case studies. In the context we're looking at the collective impact on different sectors, and also different industry sectors, the public sector, and also on policy, and also on in terms of skills and training. And so, and the impact case studies, the 500 impact case studies, of very, very rich evidence in terms of approaches, and the consultants are doing some quantitative analysis of those case studies as a set. So I haven't seen the outcome of that yet, but I'm hopeful that that will give an approach to trying to answer what you've posed is a very difficult question.
I hope it'll lead to a kind of a framework of looking at benefits, I think, as other colleagues have said, that are societal as well as financial, so that when researchers are looking at making their statement of impact, then they can be guided to think in certain terms of knowledge accretion plus economic benefit, social benefit, environmental benefit, or whatever. And I just would like to point out that I think it would be really helpful if we had more traceability of basic research, if you like, the DNA of basic research, so you can actually track as its value appreciates if it's adopted. I think we get some really good case studies that, out of that, which is a longer term, a longer wave type initiative. What we're looking at here is the immediate impact, but actually what happens further down the line, and how do we keep our eye on that original research, such as colleagues this morning were talking about some work that was done in the 19th century. Obviously things are happening more quickly now, but maybe 3 or 4 generations on, it may well be huge multiplier factors in terms of value that have been achieved.
So if I just talk about it from a sort of very practical perspective, we actually had a governance board meeting yesterday of the ICAM that we looked at this, and from one of the things we're keen on doing is to understand how the research we're doing actually maps to the business priorities that we have. And if you want to make sure that you're engaging with a company in the right way, then make sure that you're actually engaging in the things that are important to them. And for us, actually, it's quite difficult to get at those things because we know what the big problems are. And it's very interesting to go off the research programs, but actually matching them up and against what are the, you know, which are the most important ones and how we assess those priorities is quite difficult. And I think the most important thing for us is to understand, you know, are they really addressing the question in hand? And then the kind of quantifying piece of saying, is it worth... So if we had a problem with a national team that's blocking up one of our production sites in the Gulf of Mexico, that's worth billions of dollars to us. But we don't particularly want to get involved in a big game of trying to quantify how much of that research contributed to that problem. The bigger issue is to say that's a massive problem, and this piece of research really contributed to, you know, helping to solve that problem and avoid, certainly from our side, get involved into accounting exercises for, was it 10%, 20%, 30% of the value of the problem, because that way lies madness in my mind.
Mm. Yes, I mean, I think this addresses the issue to do with when you're looking at outputs versus outcomes. I would say outputs are the things that you can, often short-term things, products, the machine that goes ping that you can point to, and outcomes are the impact, the long-term, less tangible often results, which are actually in the end often more powerful but much harder to quantify. And in the BBSRC, of course, we worry about this a lot. And we kind of distinguish between gathering a lot of as much quantitative information that we can, but we temper that a great deal with stories. And what's critical is the stories, because these are the things that really persuade our funding bodies, if we will, about the value, particularly in life sciences, is very important. So that, you know, if you end up with a story that shows that you save somebody's life, then that's an incredibly powerful impact measure. I do actually worry about this a lot, because Darren Green, who now works at Microsoft, taught me a long time ago that if you want to be able to really transfer some strategic approach into operation, you need to think of 4 things simultaneously: metrics, process, organisation and culture. And if you don't think of all of these 4 simultaneously, you are doomed to failure. And if you only focus on metrics, which often we tend to, what can I measure, how many people used it, how many companies took it on board, how much money did I save, you will affect, possibly in ways you did not anticipate, culture and process and organisation, because particularly academics are really good at figuring out what the metrics are and then optimising to them. And every 4 years or 5 years we do that. And this is not a sensible way of doing a long-term research planning. So it's important to do all of these together, and I do wonder sometimes if we focus on what we consider to be the obvious thing, which is how we're going to measure it, rather than thinking about the organisation and cultural frameworks that we work in order to be able to decide what we should measure.
Steve, do you want to...
Okay, having had to wrestle with this in my ref panel, we did not use metrics, because how do you weigh a $500,000 contribution to a multi-billion turnover company to saving an SME, or maybe increasing its workforce by 10 or 20, or indeed how do you weigh some impact which has defended a market position, so there is no tangible increase, but what there is a defence against a loss, and you can't do. So in the end, it has to be subjective, and it's for this reason that the impact case studies are, in my sub-panel, were marked by several people with a discussion. So it was subjective with a discussion, and I can't see how it can be otherwise.
Yes, we're going to take 2 final points or questions. The gentleman on the left who's had his hand up for a while, and then I will ask the panel each to and/or make a final bullet point statement and answer whatever points are raised. So yes, first gentleman there, and then I'll take one other, and we'll do it all together.
Thank you. It's more of a comment, really. It's Manus O'Donnell. I am the Head of Research and Development for EDF Energy in the UK. And it's really to echo some of the points that I think I've heard. In terms of docking in some of the fundamental research, it is really important to align that with the overall business strategy. And that is where, where you go into what does quantification mean within that. And I think it's understanding the point around culture of the business, what's important to help the business within that strategy. So, for us, it's things like, are you helping us with some of the risks we perceive we have? Are there opportunities that we're missing because of the new tools and technologies you're developing? There's a key part around skills and training and the tools, making sure we've got the sharp tools to do all that, and then making sure, of course, we've got fundamental infrastructure to do it all. And where research, in my mind, fits into that is in sort of two ways. There's one way which is you're doing research which is underpinning that business strategy and helping you. And then there's another side which is what I call disruptive creativity. So you're actually challenging the strategy of the business and saying you could be doing it in a better or a different way. And that's all of value, but very, very difficult to quantify. That's my comment.
Good point. Any other final question before I ask the panel to wrap up? Okay, well, we'll take that comment and then take a quick one-liner from each of the panel on any final thoughts. Steve, do you want to start?
Yeah, I think just to repeat that not all research has to have impact. Blue Skies research is still good, and that academic colleagues should not feel, actually engineering academic colleagues should be invigorated and embraced by the concept of impact, and embrace the concept of impact.
I guess my final comment would be that impact is a personal aspect. We often think about business, long-term UK health, but in the end, research is undertaken by researchers in organisations and is received by people in businesses. So we have to think about also the personal. When it comes down to it, it's all to do with people. And that means understanding the situations and pressures that they're under, the cultural mores that they're under, and also let's not forget the most important way of doing impact and knowledge transfer is really good students moving, well-trained students moving into industry. That's your most powerful mechanism.
Bob?
So, yes, I'll just pick up on this people point. I mean, I think for things to have impact, you can't just lob things out into the ether and hope that there's someone there to catch it. I think you need to have a process where you have a really good link, whether that's policy, public engagement, whether it's something in industry, where you have someone there who you're engaging with, and then if you want to achieve level of impact, then you have someone to pass the ball to effectively. And understanding that process, I think, is really critical.
Jeremy?
I think echoing and perhaps taking a slightly different view on that, so recognising the pull versus the push or the curiosity-driven research, getting the balance right, recognising that the pull research must relate closely to business needs and strategy, and maybe academics actually getting involved with industry to help those needs become identified through road mapping or whatever it might be.
John?
Yeah, I think in 5 years' time we'll look back and we will really believe that the introduction of the REF has transformed higher education in the UK, and I think it will and is already changing the culture and of academic community and encouraging them to work closely with partners in industry, in the public sector, in the health service and in the third sector.
Interestingly enough, John O'Reilly showed us a picture earlier of the first recorded impact statement. It was Michael Faraday, that painting of Michael Faraday when he demonstrated for the first time electromagnetic induction, and a gentleman in the audience said, fascinating, Mr. Faraday, but what use is it? And he turned around and said, what use is a newborn baby? And on that note, I will thank on your behalf John, Jeremy, Bob, Carol and Steve for a fascinating contribution to the afternoon, and I'd ask you to thank them in the appropriate way. If I could ask the panel just to stay seated for a few minutes, and I'll draw my remarks to a close, and then we can all go down and take some wine. So, again, thank you all for coming. I think it's been a fascinating day. The format of the day we changed a bit from previous ones. We would value your feedback on that. Please write in. I don't know if there are any formal feedback forms in the packs, but if there are, fill them in. In your packs, you'll see that the Royal Academy is not shy in producing its own impact statements, and there are more of the same online. So these are some of the expressions we've made of why we're funding the projects and people we're funding, and what the industrial partners in particular are getting out of it. But we will continue to do that. I think it's been an interesting morning. We've had a diversity of topics. We had Paul Shearing telling us how to avoid exploding batteries by understanding what was happening inside them using X-rays and various other technologies. We had software verification for 1 billion people, an amazing thought that all this software verification was impacting. If you want an impact statement, then putting 1 billion people into your impact statement is bound to get people's attention. We had our first ever enterprise fellow talking about tagging, and not necessarily tagging criminals, but tagging most things. But knowing where your criminals are might also be a good use for such devices. We had another attempt at understanding verification, and fascinating enough, starting top down with the physical model from Helen. And again, as I said earlier, it's fascinating that that was drawing on critique and pure reason from the 19th century, and yet finding its way into very model and essential tools, and actually in that case things that avoid impact rather than create them, so even more use. John O'Reilly, so eternally grateful for John to break his intended journey to the south coast to come and join us and catch up with his wife later. This afternoon, as I said, for the first time we've tried these double acts of bringing in both the industrial sponsor to tell us what they're doing, why they're doing it, and why they need the help of the academic and the related academic. And personally, I thought that worked immensely well. I thought it was fascinating, both Formula One and diamond lasers, great stuff. And clearly, if you needed a demonstration of impact, that was it. And then, as I say, your panel have done a wonderful job and had a stimulating debate. So I will not delay the process any further. I hope you don't have to dash off to start your weekend straight away. There was some white wine getting warm downstairs and some red wine getting cold. So let's go down and take some of that. And thank you all once again for coming. Thank you.